Asdam Tambusay, and I'm honored to serve as your moderator for this session. Also, we are delighted to have all of you joining us for what promises to be an insightful discussion. So today, we have an outstanding lineup of our 4 distinguished speakers who will provide in-depth perspectives of today's webinar theme. It is my pleasure to virtually introduce you to our keynote speakers. The first one, we have Professor Iswandi Imram from Bandung Institute of Technology. The second speaker is Mr. Aung, an Executive Director at IT Solutions. The third speaker is Mr. Davy Sukamta, a Director of PT Davy Sukamta and Partners. And last but not least, we have Mr. Zia, a Coordinator in Wind Tunnel Testing and Structural Health Monitoring Unit at IT Solutions. Before we formally begin this session, I have a few announcements to make. First of all, the Q&A session will follow each speaker's presentation, so feel free to submit your questions in the Q&A box as we go. Each speaker will have approximately 30 minutes for their presentation, followed by 10 minutes for Q&A. So I will be the timekeeper to remind the speaker about their time slot. Second of all, we encourage participants to make the most of this opportunity. So please keep your questions concise and clear to allow for as many responses as possible. So, all right, to kick things off, I would like to welcome our first keynote speaker, Professor Iswandi Imram. So please join me in giving him a warm virtual welcome. So Professor Iswandi Imram will be sharing his insights on the introduction of performance-based design and some examples of its implementation in Indonesia. So a brief introduction to our distinguished speaker. Professor Iswandi Imram is a full-time professor in the Structural Engineering Research Group at Bandung Institute of Technology. He earned his Ph.D. from the University of Toronto in Canada, one of the world's most prestigious institutions for engineering and sciences. Currently, he serves as the president of the Indonesian Society of Civil and Structural Engineers, known as HAKI, and as the independent commissioner of PT Wika Beton, the largest state-owned precast concrete company in Indonesia. Besides extensive experience in high-profile projects across Indonesia, he is also an active researcher, frequently publishing in leading journals and conference proceedings. So without further ado, Professor Iswandi Imram, the virtual stage is yours. You may share your screen. Thank you very much.
Thank you. Terima kasih. Thank you also for putting a photograph of me, yeah, with younger age.
You're welcome. You're welcome, Vice.
Much younger, actually. Okay, can you see my screen now?
Yes, we can see your screen.
Okay, hold on. I make it slideshow, yeah. Okay. Okay. First of all, I'd like to thank my colleague from AIT Solution who joined also this webinar as speaker, Mr. Aung and also Mr. Zia. Thank you very much. Dan juga rekan-rekan dari HAKI, Pak Davy, ada Pak siapa lagi nih? Ada Pak Nick ya, dan lain-lain. Terima kasih juga sudah join webinar ini. Mr. Ong, I think I'll speak in Indonesia because most of the participant of this webinar is Indonesian people.
It is okay, Professor Iswandi.
All right, thank you.
Yes.
Ya, jadi sebagai pengawal ya webinar ini, saya akan mencoba menyampaikan pengenalan terhadap metode desain berbasis kinerja dan juga beberapa contoh implementasinya di Indonesia, ya approach yang selama ini sudah dicoba diterapkan di Indonesia. Ya, ya sebagai pendahuluan, metode desain berbasis kinerja di Indonesia ini sekarang sudah mulai secara bertahap ya digunakan dan juga sudah mulai berkembang ya karena memang ada hal-hal atau kebutuhan yang timbul ya kan untuk keinginan mengendalikan ataupun juga mengontrol kinerja bangunan tahan gempa ya. Dan ini juga tentunya terkait dengan fakta bahwa kita ini berada di daerah yang aktif ya secara seismik ya. Dan kita semua juga tahu bahwa dengan pendekatan PBD kita bisa menentukan ya kinerja yang kita inginkan saat terjadi gempa ya. Jadi ini pendekatan yang tadi berbasis pada kinerja dan tanpa perlu kita secara apa namanya kaku gitu ya mengikuti ketentuan code minimum yang terkadang sangat preskriptif ya dan juga sangat ingredient based ya. Nah, ini gambaran tadi yang saya sampaikan bahwa Indonesia secara seismik itu sangat aktif ya. Ini adalah gambaran rekam kegempaan yang terjadi 100 tahun terakhir. Kita bisa lihat ya, sangat banyak kejadian gempa, baik gempa dangkal maupun juga gempa dalam yang sangat mempengaruhi kita di Indonesia ini. Ya. Nah, hal ini juga tidak terlepas dari fakta bahwa kita berada di pertemuan ya beberapa lempeng dunia. Jadi kita tahu bahwa dari sebelah kiri itu ada plat Indo-Australia ya, kemudian dari utara ada Eurasia, ada Philippine Plate ya, kemudian dari sebelah timur ada Pacific Plate ya. Nah, selain itu juga di bagian darat itu banyak ditemukan active fault line ya. Kalau kita perhatikan peta bahaya gempa tahun 2010 ya, itu tercatat ada 81 active fault line yang sudah teridentifikasi. Dan angka ini ternyata meningkat ya di peta bahaya gempa 2017 di mana di situ teridentifikasi hingga 251 active fault line ya. Dan saat ini tim Pusat Nasional Gempa Indonesia juga sedang bekerja menyusun peta bahaya gempa yang terupdate ya, di mana sudah teridentifikasi sejumlah 402 ya active hotline ya. Nah, tentu saja peningkatan jumlah active hotline ini tentunya akan meningkatkan tingkat bahaya gempa yang harus diperhitungkan ya, baik saat kita mendesain maupun juga dalam kita nantinya melakukan yang namanya assessment seismik ya, atau evaluasi seismik. Nah, kalau kita mengacu pada ketentuan SNI 1726 ya, yang merupakan standar untuk perencanaan bangunan tahan gempa di Indonesia, ya kita mengenal ada level kinerja yang diharapkan ya dimiliki oleh struktur bangunan saat terkena berbagai level gempa yang mungkin terjadi. Jadi akibat gempa yang bersifat frequent sering terjadi ya harapannya kinerja bangunan untuk bangunan umum gitu ya dengan kategori risiko 2 ya bangunan biasa itu adalah immediate okupansi. Kemudian kalau terkena gempa 2/3 MCER kita nyebutnya juga kadang gempa sedang atau gempa yang mulai jarang terjadi gitu ya. Gempa desain atau DBE juga sering disebut ya. Maka kinerjanya adalah life safety ya maksimum. Begitupun kalau terkena nantinya gempa yang maksimum ya, MCER yang merupakan gempa dengan probability kemungkinan terlewati dalam masa 50 tahun sebesar 2% atau gempa 2.500 tahun, bangunan nggak boleh runtuh. Ya. Jadi maksimum kinerja yang diharapkan itu adalah collapse prevention. Ya. Nah, jadi ada pembagian kinerja gitu ya, sesuai dengan level kegempaan yang mungkin terjadi ya, di mana untuk gempa-gempa yang sering dan besarannya kecil gitu ya, bangunan diharapkan tetap elastik dan bangunan baru boleh berperilaku inelastik ada kerusakan bila mana terkena gempa kuat ya, baik itu levelnya di 2/3 MCER maupun juga gempa maksimum di level MCER ya, di mana di level kedua gempa yang besar itu harapannya perilaku struktur itu sudah berada dalam zona inelastik dan diharapkan memiliki ductility yang memadai untuk bisa tetap survive saat terkena goncangan gempa tersebut ya. Di dalam code kita juga ya eh, itu diatur bahwa kekuatan struktur ya terhadap gempa itu didesain dengan harapan sebagaimana yang tadi disampaikan ya, bahwa kalau terkena gempa frekuent bangunan kita itu tetap berperilaku elastik. Dan ini diterjemahkan di dalam ketentuan kita bahwa kekuatan struktur terhadap gempa haruslah minimum ya. Kita nyebutnya EN, Bezier nominal, sebagai nilai CS, ya, koefisien Bezier dikali dengan berat struktur, ya W. Di mana koefisien Bezier ini dihitung sebagai 2/3 MCER, yaitu gempa DBE, yang dibagi dengan faktor modifikasi respon, yaitu R atau R. Ya. Nah, nilai ini juga tidak boleh lebih kecil daripada nilai CS min dikali dengan berat struktur yang juga dikenal sebagai Bezier minimum. Nah, hanya di level itu kita melakukan desain dan perhitungan kekuatan, gitu ya. Nah, untuk mengantisipasi gempa-gempa yang besar, dipersyaratkan bangunan harus memiliki detailing yang memadai, ya. Harus punya redundancy, didesain dengan capacity design dan lain sebagainya, agar struktur bisa survive saat terkena gempa maksimum tadi, ya. Nah, namun pembuktian apakah dia bisa survive atau enggak itu enggak pernah dilakukan ya, karena kita melakukan perhitungan hanya di level tadi Bezier nominal tadi ya, bahwa secara kekuatan bangunan harus punya kekuatan yang mampu menahan Bezier nominal tadi berdasarkan demand yang dihitung gitu ya. Tapi untuk gempa-gempa yang lebih besar tidak pernah ada pembuktian ya. Jadi harapannya memang selama detailing requirement itu dipenuhi, take it for granted, bangunan akan memberikan kinerja sebagaimana yang diharapkan berdasarkan code yang berlaku. Ya. Nah, ini gambaran yang lebih detailnya ya. Jadi kalau kita lihat, kita mendesain di level Bezier nominal, ya, IN, yang merupakan DBE dibagi dengan faktor modifikasi respon struktur atau R, di mana kalau gempa terjadi di level ini ya tentu saja harapannya perilaku struktur tetap elastik ya. Kita apa namanya eh, bergantung ya pada kekuatan ya. Nah, namun pada saat gempa itu lebih besar yang terjadi, bahkan sampai level DBE atau bahkan MCER, tentunya perilaku struktur sudah akan melewati batas elastiknya. Dia sudah akan berperilaku inelastik mengikuti garis merah yang tergambar itu. Ya, jadi mulai terjadi inelastisitas ya pada struktur bangunan, ya, di mana kapasitas maksimum itu bisa termobilisir sampai mencapai Imax gitu ya, di mana Imax ini kalau berdasarkan code kita hitung sebagai faktor overstrength yang bisa diberikan oleh struktur dikali dengan gempa nominal tadi. Ya. Nah, angkanya tentu saja upper bound-nya adalah kekuatan struktur itu sendiri ya terhadap beban lateral. Ya. Nah, saat terkena gempa yang besar tadi, ya, sebagaimana yang disampaikan, timbul kerusakan pada struktur gitu ya. Di mana kerusakan ini ya kadang terukur ya, kadang sangat luar biasa, signifikan ya. Dan tentu saja dampaknya adalah ada biaya-biaya perbaikan, bahkan nanti kalau sampai kerusakannya parah sekali, bukan hanya perbaikan ya, tapi juga pembangunan ulang. Tapi on top of that, ya, ada yang namanya biaya karena terjadinya yang kita sebut dengan downtime. Ya, downtime ini adalah masa di mana struktur itu nggak bisa operasional. Ya, tergantung pada tingkat kerusakannya, semakin parah tingkat kerusakannya, semakin lama ya struktur itu tidak bisa digunakan. Nah, tentu saja ada tambahan losis biaya di sini ya, akibat struktur tidak bisa dioperasikan dalam jangka waktu tertentu. Ini yang kemudian menyebabkan total biaya yang cukup besar bila mana kita dari awal tidak bisa mengukur ataupun juga menentukan ya level-level kinerja yang kita harapkan bisa diberikan oleh struktur bangunan tersebut. Ya. Nah, ini adalah contoh ya bagaimana di Indonesia ini tentu saja ya kerusakan gempa itu menyebabkan kejadian gempa itu menyebabkan baik kerusakan struktur maupun juga non struktur bahkan juga pada building konten yang ada ya. Dan bahkan kerusakan tersebut ya kalau sudah sedemikian signifikannya, parahnya seperti yang terlihat pada gambar kiri atas dan juga kiri bawah menyebabkan bangunan itu sudah tidak layak lagi untuk diperbaiki sehingga harus dibongkar dan tentunya dibangun ulang ya. Ini sesuatu tentu saja yang akan berdampak pada tingginya biaya ataupun juga investasi yang hilang gitu ya dan tentunya ini menjadi losses. Begitupun di gambar kanan atas di mana kerusakan non struktural itu bisa terjadi dengan sangat parahnya ya. Mungkin secara struktur masih oke, tapi secara non struktural kerusakannya luar biasa sama. Ini akan menyebabkan downtime yang cukup panjang gitu ya. Ya, pernah kejadian di Palu ada bangunan yang kerusakan non strukturalnya sangat luar biasa, secara struktural masih oke, tapi downtime-nya sampai mencapai 1 tahunan lebih gitu ya, karena banyak hal yang harus diperbaiki terkait dengan elemen-elemen non struktural yang mencakup baik itu komponen arsitektural, mechanical maupun juga electrical gitu kan. Yang bawah itu memperlihatkan building content yang berantakan ya, yang tentu saja akibat goncangan, jatuh itu mengalami juga kerusakan sehingga juga timbul losis di sini. Nah, hal-hal inilah yang kemudian ya menjadi dasar motivasi ya pada awal performance base ini berkembang gitu ya. Jadi bagaimana kita bisa mendesain bangunan dengan eh, lebih baik ya mengontrol kinerja yang dapat dihasilkan oleh bangunan tadi. Ya, jadi ada yang kita sebut dengan design performance level, level kinerja yang diharapkan, yang diinginkan, dan kemudian dianalisis dan kita buktikan bahwa itu bisa dicapai. Ya, jadi di situ awalnya motivasi kenapa metode performance base ini kemudian berkembang ya hingga yang ada saat ini gitu ya. Nah, kalau kita lihat ya eh, saat kita bicara performance based prosedur gitu ya, level kinerja ya sama saja dengan apa yang tadi sudah ditetapkan di dalam ketentuan code yang sudah berlaku saat ini gitu ya. Tetap ada yang namanya operasional, immediate occupancy, life safety maupun juga collapse prevention. Nah, namun dengan pendekatan performance ini kita lebih punya kesempatan untuk bisa lebih mengontrol ya kinerja yang dihasilkan oleh bangunan saat terkena gempa ya. Jadi secara umum kalau kita bicara metode performance base ya level kekuatan ya terkadang didesain dengan pendekatan respon spektrum analisis atau analisis linear lainnya ya dengan menggunakan gempa yang memiliki probability kemungkinan terlewati dalam durasi 30 tahun sebesar 50%. Atau ini ekuivalen dengan gempa dengan periode ulang 43 tahun. Ya, jadi di level kekuatan, di level strength ya, bangunan didesain dengan memanfaatkan respon spektrum berdasarkan gempa 43 tahun tadi ya dan didesain elastik saja ya. Nah, kemudian setelah desain selesai dikerjakan ya harus dibuktikan ya apakah bangunan betul bisa memiliki kinerja sesuai dengan yang dipersyaratkan di level MCER ya. Jadi dikenakan analisis nonlinear dengan menggunakan berbagai catatan gempa yang tentu saja representatif ya untuk wilayah di mana bangunan itu berada dan dibuktikan apakah bangunan bisa survive, ya, memenuhi berbagai kriteria yang ditetapkan untuk mengukur kinerja yang dihasilkan, ya. Nah, jadi di sini agak berbeda dengan pendekatan yang selama ini kita terapkan, ya, di mana kita hanya di level strength saja. Kemudian untuk di level maksimum considered earthquake kita hanya rely pada persyaratan detailing yang sudah kita penuhi. Sementara kalau di performance base, ya, kita juga harus melakukan analisis dengan menggunakan gempa yang sesungguhnya, ya, catatan ground motion bahkan sampai mencapai 11 untuk membuktikan apakah kinerja yang dipersyaratkan itu bisa diperoleh apa enggak, ya. Nah, tentu saja kita bisa juga mengatur, ya, desain atau kinerja yang kita inginkan sesuai dengan kebutuhan, gitu ya. Dan kemudian dibuktikan, diuji, ya, sejauh mana itu bisa dipenuhi. Ya. Di beberapa provision lainnya juga bahkan juga dipersyaratkan, ya, pengecekan kinerja ini juga dilakukan di level 2/3 MCER atau di level DBE, Design Basis Earthquake, ya, untuk membuktikan apakah betul kinerja life safety itu bisa dicapai, ya, maksimumnya maksudnya, ya, tentunya diharapkan lebih kecil daripada itu, ya. Ya, ini apa namanya, tambahan informasi terkait performance based prosedur tadi, ya. Tetap kita mengacu terkait dengan kinerja, ya, pada ASCE 7 yang juga menjadi referensi utama di SNI 1726 kita. Kemudian level kegempaan, kalau kita mengacu pada TPI sebagai contoh, untuk surface level earthquake itu seperti yang tadi disampaikan, 50% probability kemungkinan terlewati dalam durasi 30 tahun atau uh, periode ulang 43 tahunan. Di mana akibat gempa ini harapannya bangunan tetap elastik, ya. Kalau bisa tidak ada kerusakan, kalaupun ada ya sifatnya minor, ya, dan bangunan bisa terus dioperasikan setelah gempa itu terjadi. Jadi kinerjanya adalah immediate okupansi, ya, bisa langsung di tempat atau dioperasikan kembali. Kemudian yang satu lagi adalah level maksimum considered earthquake, ya, risk targeted, ya, MCER, dengan 2% probability, ya, kemungkinan terlewati dalam durasi 50 tahun atau gempa dengan periode ulang 2500 tahun. Dan karena dia risk targeted, ini juga sudah dicek terkait dengan apa namanya, uh, probability untuk failure, ya, pada targeted risk 1% dalam lifespan 50 tahun, ya. Nah, akibat gempa ini maksimum kinerja adalah collapse prevention, dan struktur tentu saja akan mengalami kerusakan struktur yang cukup signifikan, ya, bahkan hampir kolaps, ya. Dan ada kemungkinan memang kalau sudah mencapai di level ini sudah tidak visible untuk diperbaiki, ya. Ada kemungkinan harus didemolisi. Tapi tentu saja kita bisa menentukan, ya, kinerja yang lebih baik lagi, ya, yang nantinya juga tentunya harus dibuktikan dengan analisis yang sifatnya non-linear, ya. Nah, perlu diketahui bahwa SNI 1726 2019 itu pada dasarnya itu sudah mengakomodasi, ya, penggunaan prosedur berbasis kinerja untuk perancangan bangunan terhadap gempa. Jadi di dalam SNI tersebut itu ada yang kita sebut dengan prosedur alternatif, ya. Ada dua prosedur yang disediakan, ada yang sifatnya itu eksplisit, ya, di mana nantinya harus dibuktikan dengan pendekatan eksplisit bahwa conditional probability untuk keruntuhan yang disebabkan oleh goncangan di level MCER itu tidak boleh melebihi 10% untuk bangunan yang masuk dalam kategori risiko 2, ya. Dan di kita kan umumnya kalau bangunan tinggi, ya, seringkali dikategorikan sebagai bangunan dengan kategori risiko 2. Selain itu juga disediakan prosedur yang sifatnya implisit, gitu ya, di mana nantinya bangunan harus memenuhi baik kriteria penerimaan yang sifatnya elemen by elemen maupun juga yang global struktur, gitu ya, saat dikenakan 11 pasang ya goncangan gempa yang tentunya dipilih dan di scale sesuai dengan kondisi kegempaan yang ada di lokasi bangunan tersebut ya. Nah, memang yang metode eksplisit ini jarang digunakan ya karena relatif sulit ya. Apa apalagi terkait dengan tadi ya untuk mencapai suatu kondisi yang betul-betul kita menyebutnya terjadi keruntuhan ataupun juga kolaps pada bangunan ya. Sehingga yang lebih banyak digunakan adalah prosedur implisit ya yang tentunya nanti harus memenuhi berbagai kriteria penerimaan baik yang sifatnya lokal maupun juga yang sifatnya global struktur ya. Jadi kalau yang eksplisit persentase tadi disebutkan secara eksplisit di bab awal ya di dalam SNI kita. Sementara untuk yang implisit itu kita bisa mengacu pada prosedur non-linear time history ya. Itu ada di bab 12 kalau tidak salah ya. Nah, kemudian juga ada persyaratan tambahan ya untuk persetujuan bangunan yang didesain dengan performance based design konsep ya berdasarkan SNI 1726 di mana DED ya termasuk juga eh, beban seismik yang dipakai ya, ground motion yang dipilih dan lain sebagainya ya, termasuk juga prosedur hitungannya itu harus di peer review oleh independent consultant yang tentunya memiliki pengalaman yang cukup ya terkait dengan penggunaan PBD untuk high rise building ya. Nah, memang proses peer review ini kalau di Jakarta ini cukup konsisten berjalan ya, dipersyaratkan oleh TPA ya, oleh TABG kalau zaman dulu kita nyebutnya ya, di mana sejauh yang saya tahu sampai saat ini memang kebanyakan peer review pada akhirnya dilakukan oleh konsultan asing ya yang memang pengalamannya sudah lebih banyak ya yang dimiliki dibandingkan dengan kita yang di Indonesia ini. Kemudian juga referensi ya yang banyak digunakan yang juga ya sudah disepakati kalau di level TPA di DKI ya itu diantaranya adalah TBI ya A.S.C 7 ini maksudnya SNI 1726 ya karena itu juga ada bab khusus ya terkait dengan global acceptance criteria maupun juga local acceptance criteria saat kita melakukan analisis nonlinear time history atau riwayat waktu termasuk juga pemodelan nantinya elemen by elemen ya itu kita bisa mengacu pada ASC 41 atau secara khusus kalau kita bicara beton itu di ACI 369.1 ya. Ya ini adalah gambaran code-code atau referensi-referensi yang tadi saya sebutkan ya ada TBI, ada ASCE 7. Kalau yang sekarang yang terbaru tahun 22 ya ini belum kita adopsi sebenarnya ya. Kemudian ASC 41 ya yang 17 itu sebenarnya sudah diadopsi menjadi SNI. Kemudian juga ASIA 369.1 juga sudah diadopsi menjadi SNI ya. SNI 7293 dan 7294 betul ya Pak Davi ya. Mungkin saya agak salah dalam penyebutan nomornya ya. Nah, kalau kita lihat ya salah satu tadi kan ada dua level lah minimal ya. Satu di strength level, satu lagi di ductility level ya. Di strength level ini yang tadi yang saya sampaikan pendekatannya umumnya adalah pendekatan linear, elastik gitu ya untuk perhitungannya. Nanti di pendekatan untuk yang ductility level tentu saja kita harus menggunakan pendekatan non-linear ya. Nah, di sini saya coba perbandingkan ya pendekatan yang ada di ASCE 7 ya ataupun SNI 1726 dan dengan PIR TBI ya yang juga menjadi acuan yang sudah diterima ya dalam kita menggunakan metode berbasis kinerja ini di Indonesia ya. Jadi kalau kita lihat metode analitis kalau di ASN 1726 masih mengacu pada metode linear saja ya, baik RSA ataupun juga linear time history analysis. Peer TBI ada pilihan kita boleh menggunakan NLTHA untuk level strength ya. Kemudian dari sisi kekuatan, ya acuan kita adalah kalau di SNI saat ini CS kali WT, ya, di mana CS-nya adalah DBE, ya, dibagi dengan R. Sementara TBI pakai 43 tahun return period. Nah, kemudian untuk strength design, untuk pondasi, ya, di kita di SNI 1726 kita mengacu pada upper strength sub zero, ya, omega sub zero. Jadi upper strength dari struktur atas yang sudah mengalami fully plastik gitu, ya, fully yielding dikali dengan kekuatan nominal Bezier. Dan ini menjadi dasar untuk merancang kekuatan pondasi, ya, atau struktur bagian bawah, ya. Sementara kalau di TBI untuk pondasi itu desainnya itu didasarkan atas MCER, di mana pondasi dianggap sebagai force control element, ya. Jadi elemen-elemen yang diharapkan tetap elastik, ya, saat terkena gempa, ya. Dia disebut dengan force control element. Nah, yang berbeda lagi adalah Bezier minimum, ya. Jadi kalau kita tetap konsisten dengan pendekatan SNI ataupun juga ASCE 7, tetap, ya, dikenakan yang namanya Bezier minimum, ya. Yang mana kalau pakai peer TBI itu tidak diharuskan kita memenuhi Bezier minimum tersebut. Nah, di kita memang dalam penerapannya ya kadang mengikuti secara penuh, ya, ASCE 7 ataupun juga ASEAN 1726, ya, untuk pendekatan desainnya. Terkadang ya menggunakan yang sudah diakomodasi oleh peer TBI, di mana kita diizinkan tidak harus memenuhi Bezier minimum. Kemudian parameter omega dan rho untuk analisis linear dengan untuk pendekatan nantinya dengan pengecekan nonlinear itu tidak dibutuhkan, ya. Jadi ini saya merahin, kenapa? Karena tetap dibutuhkan kalau kita hanya menggunakan pendekatan linear tanpa dibuktikan lewat pendekatan nonlinear. Tapi saat kita ADN akan mengkonfirmasi ulang analisis kita dengan pendekatan nonlinear, maka parameter omega dan rho ini tidak diharuskan untuk diterapkan dalam perhitungan linearnya, ya. Kemudian strength reduction factor berlaku untuk semua elemen, sementara kalau peer TBI itu hanya untuk elemen-elemen yang diharapkan tetap elastik, ya, atau force control element. Sementara elemen-elemen yang diharapkan menjadi fuse, ya, menjadi sekring, ya, menjadi tempat untuk disipasi energi, ya, itu tidak diberlakukan. Kita bisa menggunakan angka nominal, ya, bahkan nanti DCR-nya pun, ya, itu boleh kita apa namanya gunakan angka yang melebihi 1 mencapai 1,5, ya, untuk deformation control element. Karena dia nanti adalah elemen-elemen yang bakal rusak, ya, dan sudah kita siapkan dengan berbagai detailing untuk bisa tetap, ya, berfungsi, ya, sehingga dalam perhitungan linear itu diizinkan DCR-nya kita up sampai 1,5, ya. Elastic drip, ya, kalau di ketentuan SNI 2% per CD, sementara di peer TBI itu di 0,5% tanpa ada faktor CD. Nah, ini hanya memperlihatkan, ya, perbandingan saat kita diharuskan atau tetap diharuskan mengecek ataupun mendesain, ya, level strength tadi dengan menggunakan minimum Bezier coefficient, ya. Ini adalah spektrum untuk kota Jakarta yang sudah dibagi dengan faktor R sama dengan 7, ya. Faktor modifikasi respon. Di mana kalau kita lihat untuk minimum Bezier itu kira-kira nilainya adalah 3%, ya. 0,03 kalau dihitung, ya. Di mana kalau kita kemudian berhadapan dengan bangunan yang jumlah lantainya ada 70 gitu, ya, di mana fundamental periodnya mungkin sekitar 7 sampai 8 detik gitu, ya. Dan kalau kita konsisten menggunakan spektrum yang sama, maka nilai CS-nya jauh lebih rendah, ya, daripada CS minimum yang tadi disebutkan. Nah, inilah yang kadang kemudian apa namanya membuat gitu, ya, beberapa dari kita ini cenderung bagaimana kalau kita pakai pendekatan performance base gitu, ya. Menggunakan misalnya sebagai contoh gempa level SLE tadi, ya, dengan periode alang 43 tahun, ya. Apakah demand kekuatan atau demand seismic coefficient-nya bisa lebih rendah daripada ketentuan Bezier coefficient minimum tadi, ya. Sehingga kalau itu bisa dicapai, tentunya harapannya demand gaya gempa, demand Bezier yang kita perhitungkan tentunya menjadi lebih rendah, ya, sehingga bisa mendapatkan desain yang lebih optimal, gitu ya. Dan ini juga sama membandingkan berbagai level gempa, ya, baik itu DBE yang warna merah itu adalah DBE 2/3 daripada MCER yang tanpa dibagi dengan R, gitu ya. Kemudian ada gempa SLE, ya, dengan R sama dengan 1 tentu saja, ya. Kemudian ada CS min yang garis putus-putus, ya. Nah, kita lihat di situ, ya. Jadi ada masanya bangunan dengan periode yang sudah lebih panjang daripada 7 detik, gitu ya. Ternyata nilai SLE itu sudah lebih kecil daripada CS min. Ini sekali lagi nih diambil dari spektrum Jakarta ini, ya. Eh, apa namanya eh, Hanya untuk memperlihatkan, ya, dalam dalam hal-hal tertentu, gitu ya, demand gempa dari SLE itu bisa lebih rendah daripada CS min, ya. Sorry, saya mau minum sebentar, Pak Asdam. Sorry.
5 menit lagi bisa ya Pak Is ya?
Wah, saya kebut sebentar.
Iya, terima kasih.
Ya, jadi tadi udah disampaikan, ya, prosedur strength ini adalah kunci, ya, dari keberhasilan metode PBD, di mana nanti effectiveness dari strength design ini tentunya akan diukur, ya, saat bangunan kita kenakan ground motion yang di level MCER dengan pendekatan NLTHA, ya. Nah, memang yang sebenarnya ideal itu adalah kalau bisa NLTHA ini hanya sebagai sarana untuk konfirmasi saja, gitu, ya. Jadi tidak ada lagi yang namanya iterasi, gitu ya, bahwa NLTH kita lakukan ternyata masih banyak yang kurang, kita sesuaikan lagi, balik lagi, bolak-balik. Nah, itu yang sebaiknya itu kita hindari, gitu ya. Nah, tapi ini sangat bergantung, ya, pada pendekatan strength tadi, ya. Jadi ada banyak strategi yang kemudian harus diterapkan secara konsisten untuk menjamin bahwa strength level ini betul-betul nantinya menghasilkan kinerja yang baik saat terkena MCER, ya. Jadi harus betul-betul didesain secara carefully. Kemudian deformation control element, nah ini yang kadang perlu diperhatikan, ya, sebagai fuse ini jangan jangan diberi kekuatan yang berlebihan. Kalau bisa pas-pasan, makanya diizinkan sampai DCR-nya kalau kita pakai SLE itu sampai 1,5, gitu ya, supaya tidak terlalu memiliki kekuatan berlebihan, gitu ya, elemen-elemen deformation control, karena dia sebagai sekring fungsinya, ya. Kemudian force control ini yang harus kita proteksi dengan baik, dengan kekuatan yang cukup, gitu ya, agar tetap elastik saat terkena gempa, ya. Jadi kita harus menyediakan kekuatan untuk bisa mengakomodasi kekuatan paling maksimum yang mungkin terjadi pada elemen-elemen fuse, terutama di pertemuan, ya, misalnya antara lentur sama geser, beam kolom join dan lain sebagainya, gitu ya. Termasuk juga pondasi. Jadi hierarki kekuatan betul-betul harus kita jamin bisa memberikan nantinya proteksi yang memadai untuk elemen-elemen force control. Kemudian untuk pondasi, ya, yang selama ini di kita tentu saja masih pakai pendekatan ASD, ya. Nah, ini yang perlu dicatat, ya, bahwa demand untuk gaya pondasi, ya, baik under SLE ataupun MCER mestinya tidak direduksi dengan faktor 0,7 sebagaimana yang kita biasa terapkan karena kita berada di level ASD. Sementara untuk foundation bearing capacity, ya, safety factor, lateral displacement limit, ya, yang selama ini juga banyak kita terapkan pada approach yang sifatnya preskriptif, ya, kalaupun mau dipakai itu masih relevan, ya, dengan pendekatan PBD. Nah, untuk NLTHA, ya, kita bandingkan di sini cepat saja. Kalau number of ground motion-nya ya minimal 11, ya, untuk mendapatkan nantinya respon rata-rata, ya. Kemudian untuk modeling elemennya kita bisa mengacu pada ASC 41, ya, baik yang 17 ataupun yang terbaru sekarang kan ada tahun 23, ya. Dan ada juga di Asia 369.1 khusus untuk elemen beton bertulang. Inherent damping ini agak berbeda, ya, kalau kita mengacu pada SNI ini maksimum 2,5%, ya. Sementara di PRTBI tergantung pada jumlah lantai, ketinggian bangunan, ya. Minimumnya yang 2,5%. Kita bisa punya angka damping yang agak lebih tinggi untuk bangunan yang relatif lebih rendah, ya. Material strength boleh kita gunakan nilai expected, di mana nilai expected ini adalah nilai rata-rata kekuatan, ya, atau kadang juga diterjemahkan sebagai nilai karakteristik ditambah dengan 1 kali standar deviasi, ya. Kemudian kriteria penerimaan, ya, secara global sama, ya, hanya boleh ada 1 respon yang tidak memenuhi, ya, dari 11 pair gempa yang kita gunakan tadi, ya. Dan juga tentunya ada pengecekan secara lokal nantinya tergantung pada elemennya. Kalau dia force control, tentunya yang kita lihat adalah kekuatan. Kemudian untuk elemen deformation control yang kita lihat nanti adalah deformasi. Kemudian total drift, nah ini agak berbeda ya. Kalau kita mengacu pada SNI, boleh sampai 4% untuk risk kategori 2, ya. Bangunan portal misalnya, ya. Kalau bangunan dinding tentunya akan lebih kecil, ya. Sementara kalau di peer TBI itu sama rata 3%, ya. Nilai minnya tapi itu. Untuk nilai maksimum itu boleh sampai 4,5%. Maksudnya maksimum yang dihasilkan dari 11 pair gempa tadi. Ya, jadi nilai maksimum yang paling maksimum yang dihasilkan boleh sampai 4,5%. Ya. Kalau lewat itu dianggap sebagai kegagalan atau fail. Ya. Kalau lewat dari 4,5%. Kemudian residual drift kalau di SNI tidak diatur, ya, tapi di peer TBI itu diatur maksimum 1% kalau untuk nilai min, dan untuk nilai paling maksimumnya 1,5%, ya. Nah, ini beberapa advantages, ya, penggunaan PBD, ya. Mungkin apa namanya? Saya sebut beberapa saja yang penting, ya. Jadi utamanya adalah untuk mengakomodasi inovasi gitu, ya. Yang mana kadang ada sistem-sistem struktur yang tidak tercover atau belum tercover di dalam ketentuan yang ada, ya. Sehingga kita tetap bisa berinovasi tapi kemudian dibuktikan kinerjanya tetap memenuhi persyaratan yang ditetapkan, ya. Kita juga dapat menggunakan sistem-sistem struktur yang kadang di seismic design kategori D, misalnya seperti di Jakarta, itu belum terakomodasi atau malah dilarang digunakan kalau kita mengacu secara khusus pada SNI 1726, ya. Struktur sistem dengan outrigger ini kan belum tercover, ya. Atau kombinasi, ya, sistem primer seperti dinding penahan gempa dengan sistem sekunder frames penahan gravitasi gitu, ya. Jadi kalau di KDSD, kalaupun ini dipakai, ada batasan ketinggian, ya, sampai 50 meter kira-kira, ya. Jadi kalau di atas itu gimana? Mau nggak mau, ya. Kalau kita tetap ingin menggunakannya, kita hanya bisa menggunakannya dengan pendekatan PBD tadi. Atau kita menggunakan kombinasi horizontal dua seismic resisting system, misalnya frame dengan wall. Tapi bukan sebagai dual system, ya, sebagai non-dual system. Nah, ini juga sama, dibatasi ketinggian, ya, kalau untuk KDSD. Kalau dia lebih tinggi, ya mau nggak mau harus kita buktikan. Kita boleh pakai, tapi kita buktikan kinerjanya dengan pendekatan PBD tadi, ya. Dan itu kira-kira ini gambaran saja, ya. Bangunan core wall yang kadang core-nya sangat besar sekali, kemudian ada perimeter frame, ya, yang hanya 1 baris, ya, yang relatif kalau dibandingkan kekuatannya jauh, ya, di bawah yang core wall gitu, ya. Sehingga kalau kita terapkan dual system di sini, maka biasanya yang jadi masalah kita harus menambah kekuatan yang sangat luar biasa pada sistem frame perimeternya, ya, sehingga terkadang itu menjadi tidak ekonomis gitu kan. Atau yang kemudian kita pilih adalah kombinasi horizontal dinding dan frame sebagai non dual system gitu, ya. Nah, tapi kan tadi yang saya sampaikan ada keterbatasan tinggi. Ya, tapi itu nanti bisa kita siasati tadi dengan pendekatan PBD, ya. Jadi kita buktikan secara performance base bahwa kinerja yang dihasilkan sesuai dengan yang dipersyaratkan di dalam SNI kita, ya. Atau kita gunakan core wall-nya sebagai penahan gempa, perimeter frame-nya hanya sebagai sistem gravity doang gitu, ya. Dan ini banyak diterapkan di banyak negara seperti di Filipina, ya, kemudian di US gitu, di California bahkan gitu, ya. Di mana bahkan untuk platnya pun juga dibuat terkadang dengan sistem plat slab ataupun juga plat plate, ya. Kira-kira demikian. Ya, ini beberapa apa namanya catatan lah, ya, terkait dengan implementasi PBD di Indonesia saat ini, ya. Memang ada yang kemudian menggunakannya hanya untuk memverifikasi kinerja bangunan tinggi yang sudah didesain, ya. kadang juga motivasinya untuk menghindari persyaratan minimum base year ya atau CS min dikali W untuk tall building seperti yang tadi disampaikan ya. Nah, memang di sini masih ada isu yang belum apa namanya terselesaikan ya karena adanya persyaratan SNI yang tetap mewajibkan pemenuhan minimum base year tadi walaupun kita sudah mendesain dengan pendekatan NLTHA ya. Ya, jadi memang ini ada hal yang belum menjadi suatu konsensus bersama ya. Bila mana kita memang tetap diizinkan untuk apa namanya tidak memenuhi persyaratan base year minimum tersebut ya. Kemudian menggunakan structure system yang kadang belum ada di dalam ketentuan kode yang berlaku ya atau yang tidak diizinkan ya. Dan juga kadang menjadi suatu sarana untuk optimisasi gitu ya, khususnya untuk super tall building, apalagi yang terbuat dari beton bertulang gitu ya. Jadi kita banyak menjumpai di Indonesia ini karena memang masih populer material konkrit ya, bangunan-bangunan tinggi sampai 300 meter lebih gitu ya, yang masih menggunakan beton bertulang ya sebagai material konstruksinya ya. Nah, ini kan apa namanya yang kalau apa namanya kita tidak melakukan hal-hal khusus gitu ya, terkadang menghasilkan suatu kondisi penulangan yang sangat kongestif gitu ya, khususnya di elemen-elemen struktur bagian bawah ya, sehingga menyulitkan dari dalam pelaksanaannya gitu loh. Nah, disinilah kadang ya peran dari PBD juga bisa kita manfaatkan untuk bisa mengoptimasi ya. Terlepas dari tadi kita menerapkan yang namanya base year minimum atau tidak gitu ya. Terlepas dari itu tetap kita bisa melakukan optimasi ya dengan apa namanya pendekatan PBD ya untuk mengurangi rebar congestion ya pada elemen-elemen struktur yang kita rencanakan sehingga constructability-nya menjadi lebih baik ya. Nah, ini contoh saja ya, best practice mungkin bisa dikatakan belum best practice lah, tapi beberapa practice yang sudah terlihat dari berbagai implementasi ya PBD di khususnya di Jakarta ya. Memang mungkin sudah banyak diterapkan itu di Jakarta ya. Jadi yang pertama itu saat bicara strength design ya, ini masih menggunakan pendekatan SNI tadi, 2/3 MCER ataupun juga CSMIN ya, atau menggunakan nilai dari SLE ya. Tentunya ini hanya bisa dilakukan yang nomor 3 ini yang paling bawah. Kalau kita sudah punya apa namanya site specific study gitu ya untuk mendapatkan gempa di level SLE ya. Jadi ini juga kadang dijadikan dasar gitu ya untuk strength design. Kemudian karena kadang ya SLE ini juga butuh waktu untuk penyiapannya sementara apa namanya konstruksi ini dikejar pelaksanaannya ya. Tetap pondasi ya didesain dengan pendekatan preskriptif yang biasa kita gunakan, yaitu dengan memanfaatkan nilai overstrength yang dikalikan dengan nilai base shear nominal ya, termasuk juga kalau yang minimum itu yang berlaku pada bangunan ataupun pada struktur atas yang kita desain. Nah, ada juga pendekatan di mana mengambil nilai antara ya dari 2/3 MCER dibagi R ya. Ini yang tentunya berdasarkan code ya. Sorry berdasarkan nilai spektral maksud saya, sorry. Atau CS min kan. Jadi di antara dua ini ya apakah di average atau ada pembobotan gitu ya. Ini yang kemudian dijadikan dasar untuk penentuan strength level ya, untuk penentuan base shear strength dari bangunan kita. Nah, memang pendekatan ini nggak punya strong basis sama sekali ya. Tapi kalaupun dipakai ya tentunya yang selama ini kemarin pernah diterapkan ya harus dibuktikan secara eksplisit ya apakah probability of failure-nya memenuhi apa yang dipersyaratkan di dalam SNI ya, dan itu yang kemudian memang dibuktikan ternyata memenuhi probability conditional probability yang 10% tadi ya untuk bangunan dengan kategori risiko 2 ya. Nah, ini adalah beberapa praktis apa namanya mungkin kesimpulan awal lah ya dari berbagai experience yang sudah diterapkan di Indonesia dalam mengimplementasikan PBD ya, bahwa ternyata ratio base shear demand ya kalau kita bandingkan antara MCER ya dengan DBE ya itu DBE ini tentu saja maksudnya DBE yang sudah dibagi dengan R ya, itu kira-kira 2,5 sampai 2,9 ya. 2,5 sampai 2,9. Jadi kalau kita lihat angka ini dekat sekali ya dengan angka omega sub zero yang selama ini kita terapkan berdasarkan SNI 1726, di mana untuk bangunan-bangunan misalnya wall dengan frame ya, itu nilainya sama dengan 3 ya. Dan ini kalau bisa tercapai seperti ini kan artinya seperti yang tadi saya sampaikan, dalam proses desain kita belum dapat yang namanya gempa level SLE, sementara konstruksi dikejar, kita harus segera melaksanakan, sehingga pondasi mau nggak mau kita desain dengan pendekatan preskriptif gitu ya, dengan memanfaatkan omega sub zero ya, dan itu kita lakukan, dan nanti tentunya harus dibuktikan saat kita melakukan MCER, apakah betul demand gaya ke pondasi itu masih bisa mengakomodasi ya level gempa MCER tersebut gitu ya. Nah, keberhasilan ini tentu saja akan bergantung bagaimana kita mendesain upper structure. Kalau kita ngedesainnya secara efisien, ya, tidak berlebihan, ya, maka kemungkinan keberhasilannya akan tinggi. Justru kalau kemudian kita desainnya agak ceroboh, ya, elemen-elemen yang diharapkan sebagai fuse, sebagai sekring, ya, tidak kita perhatikan secara seksama, banyak overstrength yang kemudian kita hasilkan. Nah, itu otomatis nanti overstrength yang dihasilkan bisa melebihi faktor 3 tersebut. Dan itu kemudian kalau terjadi ya kalau di awal kita sudah mengasumsikan maksimum 3, kenyataannya bisa lebih dari 3, ya tentu saja akan jadi masalah saat bangunan itu kita kenakan MCER. Ya, demand ke pondasinya bisa lebih besar daripada yang kita asumsikan di awal. Ya, kira-kira begitu. Ya, ini gambarannya ya. Jadi apa namanya? eh, QEH ini adalah base demand dari upper structure yang sudah fully yielded ya, di mana dikalikan dengan omega sub zero, asumsinya dari 3 ya, ini yang kemudian dipakai sebagai dasar kita untuk mendesain kekuatan pondasi di bawah bangunan ya. Tapi keberhasilannya tadi sekali lagi bergantung pada nilai aktual dari kuat lebih struktur atas kita ya. Sebagai penutup ya, ini hanya menggambarkan beberapa contoh ya bangunan-bangunan di Indonesia, khususnya di Jakarta, yang didesain dengan menggunakan PBD. Ya, jadi ada di situ ada autograph tower. Ini saat ini menjadi bangunan yang tertinggi di Indonesia dan juga tertinggi di Southern Hemisphere ya, di selatan apa namanya bumi ya, dengan total height itu 385 meter. Kemudian di sebelahnya ada Luminary Tower ya, total ketinggian 304 meter. Ya, ini yang ngedesain dulu almarhum Pak Bambang Budiono. Kemudian Indonesia One, ya, total height 303 meter, yang mungkin akan dibahas juga oleh Pak Dapi pada hari ini ya, karena beliau yang ngedesain Indonesia One ini. Kemudian ada Wisma Sudirman, ya, sampai 260 meter, Ciputra Tower 250, Oasis Central 320 ya. Ini rasanya semuanya didesain oleh grup PTW ya, PTW Ratman Associate. Nah, perlu dicatat juga bahwa PBD ini juga belakangan banyak dipakai ya sebagai sarana untuk mengakses bangunan-bangunan existing ya, terutama bangunan-bangunan yang secara ingredient ya, secara ingredient atau preskriptif itu nggak memenuhi syarat-syarat ketentuan minimum yang berlaku di dalam peraturan yang ada ya. Nah, kalau udah seperti itu memang pendekatan yang lebih masuk akal untuk mengevaluasi ya, kemampuan struktur untuk survive saat terkena goncangan gempa itu adalah pendekatan performance base ya. Dan ini sudah banyak diterapkan di beberapa bangunan ya, baik di Jakarta maupun juga di tempat lain ya, terutama saat terjadi kondisi kegempaan yang cukup merusak, yang kemudian mengharuskan kita mengevaluasi ya bangunan-bangunan yang bertahan sejauh mana dia masih punya kemampuan untuk bisa mengantisipasi gempa-gempa yang mungkin terjadi in the future ya. Kira-kira demikian, saya kembalikan ke Pak Asdam ya. Terima kasih atas perhatiannya.
Terima kasih banyak Pak Iswandi. What an insightful presentation from our first speaker. As promised, we now open the floor for questions. Let me go through the chat box. We've got 5 questions in total, Pak Iswandi.
Ya,
Mungkin
mangga.
dalam bahasa Indonesia ya Pak.
Ya.
Yang pertama, apakah diizinkan mendesain bangunan baru di bawah persyaratan detailing minimum? Misal, struktur beton SRPMK, spasi sengkangnya didesain lebih renggang dibandingkan ketentuan dari spasi sengkang minimum SRPMK yang tercantum dalam SNI. Dan landasan performance point-nya masih tercapai setelah struktur dianalisis menggunakan PBD. Seperti itu, Pak. Mungkin itu dulu, Pak, bisa ditanggapi.
Ya, jadi yang pertama harus dicatat gitu ya. eh, dengan pendekatan PBD ini memang harapannya tetap ya kalau kita bicara persyaratan detailing untuk bangunan baru ya itu tetap harus kita penuhi semaksimal yang memang ditetapkan oleh ketentuan yang berlaku. Khusus untuk bangunan-bangunan existing yang memang dari awal secara preskriptif, secara ingredient gitu ya, karena memang saat itu belum berlaku ketentuan-ketentuan yang apa namanya yang eh, khusus ya terkait dengan seismic detailing. Nah, ini diizinkan ya. Nah, cuman yang jadi problem adalah ya termasuk untuk bangunan baru kalau misalnya kita tidak ingin mengikuti ketentuan detailing yang ketat tadi gitu ya. Bagaimana kita bisa mendapatkan eh, kurva backbone yang representatif gitu ya. Jadi kurva backbone yang representatif ya, yang betul-betul menggambarkan segala kekurangan gitu ya yang ada pada detailing yang kita terapkan tadi ya. Kalau kemudian kekurangannya nggak banyak, mungkin masih lebih mudah ya. Kita menurunkan backbone curve tadi, termasuk juga tentunya backbone curve tadi kan tidak hanya kita bicara backbone curve yang sifatnya monotonik ya, tapi justru yang sudah juga memperhitungkan efek siklik ya yang bakal terjadi saat ada gempa yang tentunya akan menurunkan kapasitas deformasi daripada elemen tadi dan juga kekuatannya gitu ya. Jadi dari sisi kekuatan ada reduksi, dari sisi deformasi ada reduksi gitu ya. Nah, saat kita misalnya tadi katanya SRPMK akan menjadi misalnya SRPMB. Nah, ini kan reduksi ductility-nya sangat luar biasa ya. Dan akibatnya nanti kemampuan deformability ya yang bisa diberikan itu juga sangat pendek sekali. Jadi kalau kita mengacu misalnya pada ASCE 41 ya, kita bisa bandingkan tuh antara elemen-elemen yang comply dengan ketentuan detailing yang ada di code dengan elemen-elemen yang nggak comply. Dan yang nggak comply-nya pun juga hanya misalnya ya terkait dengan anchorage atau terkait dengan apa namanya gesernya tidak dicek terhadap hierarki yang ada misalnya ya. Itu perbedaan deformability-nya tuh sudah sangat luar biasa ya. Perbedaan deformability-nya sangat-sangat luar biasa ya. Nah, artinya kalaupun kita paksakan untuk daerah yang gempanya gede gitu ya, seperti Jakarta gitu ya, atau bahkan yang lebih besar lagi misalnya di Sumatera Barat gitu ya, maka udah pasti waktu kita lakukan hitungan ya sulit untuk bisa memenuhi demand gempa MCER yang gede tadi gitu loh. Jadi perlu dicatat ya, saat kita ngedesain di strength level, pendekatan preskriptif aja misalnya sebagai contoh ya, untuk SPMK misalnya kan, kita kan bagi gempa tadi, gempa DBE ya, yang kita bagi itu gempa DBE. Kita bagi gempa DBE ya dengan R. Dan ingat, gempa DBE itu 2/3 dari gempa MCER. Jadi kita sudah kalikan 2/3 untuk masuk ke level DBE dari MCER, kemudian kita bagi 8 lagi gitu. Artinya gempa MCER itu kita bagi 12 kan? Kan 2/3 8, jadi 2/24, berarti 1/12. Nah, bisa dibayangkan kan, kita mendesain bangunan dengan kekuatan hanya 1/12 dari gempa MCER. Bagaimana bangunan kita bisa survive kalau detailingnya hanyalah SRPMM? Ya, bagaimana bangunan kita bisa survive kalau detailingnya SRPMB gitu kira-kira gitu ya. Nah, jadi apa namanya eh, ya tentu saja tadi ya pada saat kita tentukan SRPMM kan bukan pembaginya bukan 8 ya, otomatis 5 pembaginya ya. Tadi saya mungkin agak sedikit miss di situ. Pembaginya 5 ya, tapi tetap ya 2/3 5 berarti 2/15 1/7 atau 1/8 kira-kira. Jadi gempa yang bakal datang 8 kali lebih besar dari kekuatan yang kita sediakan ya. Kalau nggak punya detailing yang khusus ya, akan sulit dia bisa survive. Kalau dia tidak didesain dengan kan kalau kita pakai SRPM ya, kita tidak perlu ngecek lagi yang namanya hierarki strong column weak beam ya. Karena strong column weak beam kan kita cek kalau kita di SRPMK. Nah, saat kita di SRPMM kita nggak perlu cek. Nah, tapi kan akibatnya tadi, waduh, dengan 8 kali lebih besar, ya pasti fail. Jadi sekali lagi yang saya sampaikan, kalau mau dicoba-coba boleh ya, tapi rasanya nggak akan bisa berhasil ya, nggak akan bisa berhasil karena tidak realistik pendekatan itu ya. Nah kecuali, nah ini ya kita punya sistem mekanisme disipasi lain ya, misalnya kita sekarang ini kan di Indonesia ini kan, kalaupun kita pakai base isolation misalnya sebagai contoh ya, kemudian bangunan kita KDS-nya D ya, kalau kita konsisten dengan SN maka dengan base isolation KDSD tetap detailingnya harus spesial ya untuk bangunan tinggi. Nah, ini kadang menjadi pertanyaan, Pak, kan sudah ada fuse di situ, sudah ada disipasi, mekanisme disipasi yang baik. Kenapa tetap harus pakai KDS apa detailing yang khusus gitu kan? Nah, di sini ya masih ada peluang sebenarnya ya, kalau ada kajian yang mendalam tentu saja harus dibuktikan ya. Bahkan pembuktiannya kalau bisa secara eksplisit ya, dibuktikan bahwa conditional probability untuk collapse-nya itu ya sesuai dengan ketentuan yang berlaku gitu loh. Kira-kira begitu ya jawaban saya ya, tapi intinya enggak ada realistik.
Baik, terima kasih banyak Prof. Iswandi Imran. Semoga Pak Stefan Wibowo pertanyaannya terjawab. Mungkin satu lagi ya Pak Is ya. Ada yang
Mangga.
menarik, ya ada yang menarik dari pertanyaan partisipan Pak Johannes. Apakah untuk evaluasi dengan 11 ground motion harus mengikuti gempa-gempa yang disebutkan di SNI 1726 atau boleh dengan ground motion lain asal sudah diskalakan dengan match response spectrum saja?
Ya, jadi memang prosedurnya kita kan nggak punya catatan gempa ya di Indonesia ini ya, yang komprehensif lah gitu ya. Nah, sebenarnya kan sudah ada yang namanya buku peta de-aggregation gitu ya, yang dikeluarkan oleh Pusat Gempa Nasional ya, di mana itu bisa menjadi guideline ya. Kemudian juga ada SNI terkait dengan selected dan apa ya, ground motion ya, itu yang Pak Davi dan kawan-kawan yang sudah juga membuatkan gitu ya. Nah, ini bisa dijadikan acuan di mana catatan gempa yang tentunya ada apa namanya parameter-parameter yang kita lihat gitu ya untuk memilih catatan gempa yang sesuai kan, kalau dalam bahasa SNI kita itu kan gempa yang digunakan itu kan yang memiliki karakteristik yang mirip gitu ya. Nah, kalau kita bicara karakteristik kan mekanismenya, jaraknya, magnitudenya gitu ya. Nah, hal-hal itulah yang kemudian bisa kita pilih dengan mengacu salah satunya pada tadi buku deagregasi yang sudah mencoba memisahkan ya mekanisme-mekanisme gempa dengan jarak dan magnitudnya untuk berbagai wilayah di Indonesia gitu loh. Jadi ini suatu panduan yang sangat-sangat berguna ya, eh, bisa dipakai ya untuk tadi ya kan, kalau kita bicara satu wilayah, satu daerah, mungkin ada beberapa mekanisme yang bisa mempengaruhi ya kondisi kegempaan di situ ya, mulai dari yang namanya apa namanya megatrust ya, penioff ya, ataupun juga shallow crustal gitu ya. Nah, nanti tinggal dipilih yang sesuai dengan apa mana yang lebih dominan ya mempengaruhi wilayah tersebut gitu kan. Dan biasanya ya tetap kita ada wakil dari masing-masing mekanisme kalau memang itu mempengaruhi wilayah di mana bangunan yang sedang kita evaluasi itu berada gitu. Nah, selanjutnya ya dilakukanlah yang namanya scaling dan lain sebagainya gitu. Kira-kira begitu ya. Jadi panduannya sudah cukup baik ya untuk dimanfaatkan untuk tujuan tadi ya, memilih dan juga menskalakan. gempanya sehingga betul-betul menggambarkan kondisi kegempaan di wilayah di mana bangunan itu sedang kita evaluasi.
Baik, baik. Ya, terima kasih banyak, Prof. Iswandi Imran. Sebenarnya pertanyaannya masih cukup banyak, cuma karena waktunya sudah tidak memungkinkan, mungkin kita lanjut ke speaker berikutnya ya Pak Is ya.
Enggak, nanti mungkin kalau bisa
Catat.
apa ya, bisa
Ya,
didokumentasikan lah
ya,
list pertanyaannya nanti dikirim ke saya coba
ya.
nantinya jawab, mungkin nanti di post di websitenya HAKI ya.
Iya, teman-teman dari HAKI mohon ya, bantuannya ya, Pak Andreas dan tim.
Ya, terima kasih
Ya, terima
sekali
kasih.
lagi ya.
Ya,
Terima kasih
Pak.
juga atas perhatian teman-teman sekalian. Semoga apa yang saya sampaikan ini bisa bermanfaat untuk semua.
So, Professor Iswandi Imran, once again, thank you very much for sharing your expertise and valuable insights on this topic. I'm sure the audience has gained key takeaways from your presentation that will be beneficial in understanding performance-based design. So, all right, moving on to our second keynote speaker, Mr. Aung. Just want to check if you're here.
Yes.
Okay, yeah. So everyone, please join me in giving him a warm virtual welcome. Okay. So Mr. Aung will be sharing his insights on designing more resilient and less vulnerable buildings using performance-based design approach. So a brief introduction to our second speaker. Mr. Aung is currently the Executive Director of AIT Solutions. In over 16 years of his professional experience, Mr. Aung has been involved in over 150 tall building projects across Asian countries, including Thailand, the Philippines, India, to name a few. In these projects, Mr. Aung has led the structural engineering team at IT Solutions and provided solutions and services in performance-based seismic design, wind engineering studies, and real-time structural health monitoring. Apart from projects, Mr. Aung has authored and co-authored several research papers, some of which include smart system for smart structures, performance-based seismic design of reinforced concrete dual system building, smart system for structural response control, and lastly, preliminary design of tall buildings using artificial neural networks. So without any further ado, let's give it up to Mr. Aung. You may share your screen, Mr. Aung.
Thank you. Thank you, Dr. Asdam, for your kind introduction. Let me share my screen. Can you see my screen?
Yes, we can see
Okay.
your screen. Perfect.
Okay. Good morning, everyone. Today, I will present our practice in carrying out performance-based seismic design of tall buildings. So when we carry out the structural design of buildings after completion of architectural form development, we have to develop the structural system. Generally, in the code, commonly used structural systems are bearing wall system, building frame system, jewel system, moment frame system, and cantilever column system. They are for the seismic force resisting systems. Bearing wall system, we design for the walls to carry the 100% of gravity loads as well as the 100% of lateral loads. In building frame system, we design the walls to carry 100% of the lateral loads and the frame carry only the gravity loads. For moment frame, it carries both gravity and lateral loads. But dual system, walls and frames are carrying lateral loads together. But for cantilever column system, we use for the small structures like the garages. So in tall buildings, most of our structural systems are based on those common structural systems. In A.Sc. 7, there are more than 80 types of structural systems. Here, there are some structural forms that we normally use in the design of tall buildings. Sometimes we use the bearing walls. If the lateral stiffness is not adequate, we also add the outrigger systems together with the bearing walls. And also we use the dual systems, which comprise of shear walls and moment resisting frames. So let me briefly talk about the seismic design concept. The current seismic design, the building code's objectives are to prevent the buildings from causing large-scale loss of human life and in earthquakes. So our main priority is safety, public safety. So when we design the seismic design of the buildings, for the normal residential buildings, we allow damage in the buildings under strong earthquakes. We do not design the normal buildings to remain elastic or no damage at all during the strong earthquakes, because earthquake may not happen during those strong earthquakes may not happen during the lifetime of the building. So if we design to remain elastic, in that case, our design may not be economical. So what we do is we allow some damage, but the building should not collapse under strong earthquake. And also the buildings should be serviceable under frequent earthquakes. So in this figure, x-axis is the lateral displacement, roof drift of the building, and y-axis is the seismic force base shear of the building. So if we design the building, let's say, if we design the building to remain elastic, the force and the displacement relationship will be linear as shown in the blue line. If the force increase, the displacement increase linearly. But when we do the design, we do not design for the elastic base shear. So we design elastic base shear VE. So when we design the building, we reduce the base shear by the response modification coefficient, which is based on the ductility and toughness of the structural system. So we reduce the base shear VE divided by R, and we got the design base shear. There will be minimum base shear, design base shear requirement in the code. So after getting the design base shear, we design the building and we provide the longitudinal reinforcement in the beams, vertical reinforcement in the columns for the flexure response, and also shear reinforcement in the members. And we design those reinforcement based on the design base shear V. And also we provide the detailing requirements according to the structural system that we selected. So when strong earthquake happened, the actual base shear will be more than our design base shear. So when the members reach their yielding capacity, they will start yielding. So the structure becomes nonlinear. The structure behaves inelastically. The force is not increasing substantially like elastic response, but displacement increased substantially. So to carry the gravity loads on our structural system and the large displacement, the ductility is important. So we have to provide the ductility, ductile detailing requirements in our structural systems. So in our analysis, normally we carry out the linear analysis when we do the code-based design. So when we apply the design base shear V, we will get the displacement, which is delta E divided by R. So our analysis domain is only in the yellow region, only in the elastic analysis domain. We cannot capture the actual response of the building which is inelastically, which has the inelastic response. So the inelastic response region, the purple region, is not explicitly simulated or checked in our normal code-based design procedure. So we just implicitly, we just assume that if we design the building according to the design base year and provide the tactile detailing, our building will not collapse under strong earthquakes, and also our building will be serviceable under frequent earthquake. But there is no explicit evaluation in the analysis. And another thing is, after reaching the yielding capacity of the members, the base, the shear demand still increase. The curve is not flattened suddenly. There is a overstrength effect, which we normally estimate with the overstrength factor omega naught. That overstrength effect is coming from the material overstrength, which is in which we use the nominal material properties in our design, but actual properties of the materials will be more than that. For example, the rebar strength, yield strength, the nominal strength, and the actual test strength will be different. Not only that, we have the safety margin in our design. We leave the safety margin TC ratios 0.8, 0.9 in the design of members. And also we have the load factors, overstrength. We have the load factors and also strength with reduction factors phi in our design. Those effects generate the overstrength, and it will increase the base year, which will reach the Vmax. To estimate that maximum shear demand in our system, we have to multiply our design forces with omega naught. Those forces, those amplification we mainly use in the important structural systems to resist the maximum demand forces, not all the members. And also we estimate the inelastic lateral displacement or drift using multiply with the CD deflection amplification factor, because we have to check our lateral drift, whether it is within the acceptable limits or not. Between 1987 and 1994, there are several earthquakes in California. So Structural Engineering Association of California and FEMA, they developed the framework to enable the engineers to design the buildings with predictable seismic performance and also enhance the performance objectives in the basis for design relative to those underlying in the contemporary building codes. So that project called Vision 2000. And then they developed the design procedure, which now we call it performance-based design. So compared to the code-based prescriptive design and performance-based design, in code-based design, we have to follow the prescriptive criteria mentioned in the code. And the engineers do not have the ability to evaluate the actual performance which is intended by the code. And also there are limitations in the use of structural systems. So mostly the code-based procedures, we presume if we conform the building code, the performance will be obtained. On the other hand, in performance-based design approach, we check the building performance explicitly under different levels of earthquake. And also we can substantiate, we can ignore the code prescribed requirements if we can prove that our building performance is meeting the code intended objective. And also if we want to use the innovative structural systems or devices, we can also prove with the performance-based seismic design approach. Finally, performance-based design can also provide us the cost-effective design. For example, in A.Sc. 7, if we want to use the bearing wall systems in high seismic zone, there is a height limitation, 160 feet. If we want to use in the tall buildings, we cannot use those bearing wall systems. Tall bearing shear wall with the flat slab system, we can use only for the 16-story building. So if we want to use those systems, we have to prove by performance-based design approach. So in this architectural form, if we design according to the code base, we need to use the dual system, which has no height limit. So in that case, we need to provide the moment frame and the shear wall. But if we can prove with the BBD using that bearing wall system only with the flat slab, we can achieve the cost-effective design. Not only that, we can have the clean structural system compared to the dual system. So this is the comparison of the structural system with the moment frame and the flat slab. Another thing is the overstrength factor, omega naught. If we have the transfer system where the discontinuity happen in the lateral system, in that case, we have to design those members with the overstrength factor. So in the code, overstrength factor is about 2.5. But if we design with the performance-based seismic design approach, we do not need to consider those prescribed factors. We can explicitly estimate the force demand in those members in the nonlinear analysis procedure. And also we can use the innovative systems like the dampers, like viscoelastic coupling dampers or phase isolation. So we can prove those devices' effectiveness using the performance-based design approach. In terms of cost effectiveness, for example, in the shear walls, we have to provide the confinement reinforcement at the boundary zone in the code-based design approach. But if we can prove that in our BBD analysis, nonlinear analysis, if the shear wall axial strains are not large, we can relax the shear wall confinement in those stories. So it will have the cost saving. So here is the comparison between code-based confinement layout and the BBD confinement layout. In BBD, the confinement is relaxed and it is not congested. It will also help improve the constructability requirements. So when we carry out performance-based seismic design, we need additional information compared to the code-based design. Normally, in the code-based design, we have to prepare the design criteria, which we call basis of design. In BBD also, we need to prepare that document, but we have to consider the seismic input, additional seismic input information, and also performance objectives and acceptance criteria based on BBD procedure. And geotechnical investigation, normally we conduct in the code-based design as well. So from geotechnical investigation, we have to get the soil type for the seismic loading, allowable bearing capacity. If there is a soft soil site with the liquefaction potential, we have to check. And important one is in BBD, we have to engage another consultant. We call it PSHA consultant. We have to conduct the site-specific probabilistic seismic hazard assessment. So that consultant carry out the seismic hazard analysis and provide the structural engineer with the recommended response spectra for service level earthquake, design earthquake, and maximum considered earthquake. And also they provide the ground motions to be used in the nonlinear time history analysis for maximum considered earthquake. If our site is at the soft soil site, they also conduct the site response analysis to check the amplification effect of the soft soil layers. Normally in code-based design, we amplify the soft soil effect with the code prescribed factors, FA, FE value according to A.Sc. 7. For the tall buildings, wind tunnel test is also important. Wind tunnel consultant provide the floor acceleration and also the floor-by-floor wind load to be used in the structural analysis. So normally they provide the 10-year return period wind for service level wind check, for the story drift, lateral displacement, and for the ultimate strength design of the members for calculation of reinforcement, they provide the 700-year return period wind. And also they conduct the natural frequency sensitivity study because our finite element model's natural period may not be exactly matching with the actual building natural period. So they're changing the natural frequency of the building and provide the force demand and acceleration. Here are some good reference for performance-based seismic design and also wind design. Currently, the latest PBD guideline is LED BSDC 2023 with 2024 supplements. This is from Los Angeles Tall Building Structural Design Council. Together with those guidelines, we also use the ASCE 41 guideline in modeling for the nonlinear modeling parameters. So in seismic hazard assessment, PSHA consultant normally provide three response spectra, which is maximum considered earthquake, which has 2475-year return period with 5% damping, and design earthquake, which is 2/3 of MCE, and service level earthquake, which is 43-year return period. But for service level earthquake, the damping varies with the height. For the tall buildings, damping will not be always 2.5% damping. It will be lower than that. Maybe it is about between 1.5% to 2%. So for seismic performance objective, this is the code minimum intended objective. We have to check for service level earthquake with the performance objective. To satisfy the serviceability requirement, the structure has to remain essentially elastic and minor cracking in the concrete and damage. For maximum considered earthquake, we have to check for the collapse prevention requirement. The structure should not collapse, and the extreme earthquakes, it will have damage, but may or may not be repairable. So in PBD procedure, first we have to get the geotechnical investigation results. And also after getting the geotechnical investigation results, we have to engage the PSHA consultant and provide the geotechnical assessment to PSHA consultant. During that time, we can develop the structural system in schematic design stage. After getting the structural system preliminary finite element model, we have to provide the dynamic properties to the wind tunnel consultant, model analysis results to the wind tunnel consultant. So wind tunnel consultant will carry out the structural load test and use post-process their results with those dynamic properties and provide the wind loading to the structural engineer. So structural engineer will carry out the initial elastic design using that wind loading and SLE loading from PSHA consultant and get the initial reinforcement. Then carry out the nonlinear evaluation, create the nonlinear model, and check the MCE level evaluation. So in design process, in the initial design stage, structural components are designed for the maximum of wind and service level earthquake demand. But some structural members like shear wall, shear design, if we determine the shear wall thickness based on the wind and SLE demand, it may be small. It may not be adequate for the MCE demand. So those kind of components, we check the demand based on the response spectrum, MCE level response spectrum analysis using experience factors with our value. We divide by the MCE elastic demand with the experience factors, R values. Then we get the reinforcement information to be used in the nonlinear model. Then in MC evaluation, we create the nonlinear model and analyze the time history analysis. So in SLE evaluation, we have to contact the response spectrum analysis and create the linear FEM model. And accidental eccentricities are not considered in service level evaluation. And critical damping is between 1.5 to 2.5%. And also, we do not consider our omega naught rho factor and CD factors. And also, we do not scale down the SLE base year to the to the equivalent static base year with the R factor. Because in SLE level earthquake, we want to design the building to remain elastic. So there is no scaling for base year. For acceptance criteria, we check the drift limit and also DC ratios for depending upon the deformation and force control actions. For drift limit, we use 0.5%. For MCE level evaluation, we conduct the nonlinear time history analysis. Mostly we use 11 pairs of ground motion record. And for damping, we use 2.4% constant modal damping with small amount of relay damping for unmodeled energy dissipation. And we use the average demands of 11 ground motion records. So in nonlinear response and modeling, we have to model the backbone curve parameters for our structural components. For example, in this figure, x-axis is rotation of the beam, and y-axis is the moment demand. So x-axis present the rotation in radian. So during the laboratory test, if we reach the yielding moment capacity, the moment demand doesn't increase significantly, but rotation is increased. So we apply the cyclic load and then we develop the backbone curve. So normally structural engineers familiar with the strength capacity check, calculate the moment demand and calculate the moment capacity. We understand that, but for the rotation demand and rotation capacity, we are not familiar with. This rotation capacity is determined mainly from the laboratory test. We can generate the rotation, we can calculate the moment rotation capacity based on the moment curvature curve section analysis, but we normally use the laboratory test results because it is a cyclic loading. It has the effect of the shear demand as well. So these are the sample test figures for different rotation demand level. So we need to know what is the damage state of the rotation demand as well, because we are checking the rotation in some components in performance-based design approach. So when we classify the actions for the deformation control and critical deformation control and force control action, we have to think based on their response. So if the response is tactile, for example, flexure response of the beam, after yielding due to flexure bending moment, the beam will not fail suddenly. So we consider that action as a deformation control action. For the brittle actions like shear response, shear failure, we consider as force control action. So for deformation control action, we can get the backbone curve parameters from the ASCE 41 document. Here are sample parameters for the backbone curve for the beams. So on the red box side, there are modeling parameters to develop the backbone curve. On the right side, in the blue box, it is the acceptance criteria to check whether our rotation demands are within the limits or not. So if we check for the collapse prevention performance level, we have to check with the CP performance criteria. Here are some acceptance criteria for global response as well as the local response. I will not explain details. Professor Iswandi already showed the acceptance criteria in his presentation. So after analyzing the nonlinear time history analysis, we have to check the global response first. We have to compare the base year, story drifts, whether the results are reasonable and acceptance within the acceptance limits or not. For the base shear here, I compared the base shear for elastic MCE base shear, inelastic MCE base shear, and SLE base shear. So inelastic MCE base shear, the green one should be lower than the yellow one. So here the base shear is approximately half of the elastic base shear, but SLE base shear is significantly low. On the right side, it is based on percentage of the weight of the building. So if the green bar is larger than the yellow one, larger than the elastic base shear, our analysis is something wrong. We have to recheck our model. And this is the sample output of the transient drift that we check. The average drift limit is 3%, the solid red line. So the average value is the black line from the ground motion records. And here is the residual drift check. So residual drift we check at the last step of the analysis. For residual drift check, we need to analyze the building maybe 2-3 cycles, at least 2-3 cycles beyond the ground shaking, after the ground shaking stop. Because ground shaking stop, but the building may still shake after the ground shaking. So we need to analyze that effect in our nonlinear time history analysis and check the permanent drift. So the drift limit is 1% for average limit. For individual, it is 1.5%. And for the local responses, we have to check the shear walls for the deformation capacity requirement. Normally, we check the axial strains for the flexural deformation, but for the shear response, we check the shear capacity with respect to the shear demand. So here are the sample plots of one location of the shear wall. So at one corner of the shear wall, we have to check all corners of the shear wall. Here is the sample results for one corner. So on the left side, it shows the axial strain, compressive strain of concrete. On the right side, we show the tensile strain of the vertical rebar. So x-axis is the strain value, y-axis is the story level. So compressive strain, for the unconfined concrete, we limit the strain to 0.003. On the right side, we check the tensile strain, but the rebar yielding strain 0.002 is not a limit. Actual limit is 0.05 for the rupture strain. It is very far from that. So we can see that in one ground motion, the shear wall is yielding in flexure at the base. For coupling beams, we have to check the flexure rotation for the conventional reinforced coupling beam. For the shear, we consider as a critical force control action. Normally, when we check the shear in the beams, we check the probable shear based on the capacity-based design approach. For diagonal reinforced coupling beam, we check the shear deformation as a deformation control action. Here is the sample result of one coupling beam along the height of the building. And the black one is the average demand, and the red line is the rotation limit. X-axis is the coupling beam rotation demands in radian. For the moment frames beams, we check the flexure rotation as a deformation control action and shear demand as a force control action. For the columns, we check the axial demand as a compressive demand as a force control rotation for the PMM action, and shear capacity is checked as the force control action. For the flat slab, we check the flexure rotation of the flat slab as a deformation control action. So to model the flat slab nonlinearity, we have to model the equivalent slab beam with the frame element and provide the moment hinges at the end of the beams. Then we check the rotation. That rotation capacity depending upon the punching shear demand to capacity ratio. For the diaphragms, in plane stresses in the slabs, we check the collector, reinforcement, shear friction, chord, and axial and shear. All are force control actions. So for mat foundation, we have to check for the bearing capacity, geotechnical capacity, and also the strength capacity requirements for flexure and shear capacity. So for mat foundation design, we consider all actions as a force control action. For shear capacity, we have to check for the one-way and two-way shear. For basement walls, normally people design the basement wall to resist the lateral pressure for the out-of-plane action. But we also need to check the in-plane response as well, like a shear wall shear. So in-plane shear needs to be checked. So we have to check the both in-plane and out-of-plane shear capacity, and also the flexure capacity, out-of-plane flexure capacity of the basement walls as force control actions. So in PBD, it is that design approach is the evolving topic. So we have to learn, do the continuous learning, and also in our design, we need another person to review our work, which is in which we are doing right or not, because we are doing beyond the code. So peer reviewer needs to be engaged, and not only that engagement will also promote the exchange in the idea and also the knowledge sharing between peer reviewer and the structural engineer of record. And also we can enhance the body of our knowledge for the firms practicing PBT. Normally, peer review should engage at the early stage of the structural design phase. And during the peer review process, peer reviewer develop the peer review comment log and also set up the timing and peer review milestones. So that's all for my presentation about the performance-based seismic design. So I'm happy to take the questions if you have any questions.
Thank you so much, Mr. Aung. That was a truly engaging presentation from you. So as mentioned earlier by Mr. Aung, we now invite questions from the audience. So you've seen some questions from the Q&A box here, Mr. Aung. So
Yes.
do you mind if I read it for you, or do you want to read it yourself?
And let me read.
Okay, so we've got like number of questions here from
Okay.
Danigo, from some from anonymous attendee as well.
Okay. So question number 1 is there an explicit procedure for calculating the conditional probability of failure as required for performance-based design in SNI?
I think that was for Professor Iswandi.
I see.
I think for your questions is regarding less dense reinforcement for shear wall boundaries. How do you model the reduced rebar SW in the FEM software, finite element method software? As far as I know, SEA 41 provides some modeling parameters, for example, backbone curves, but these parameters, I assume, are mostly for element that is designed to be code compliant. Thus, if you use element for shear wall in this context that has reduced detailing, for example, reduced confinement in the shear wall, how can we be adequately model that in the software, assuming we're not going to be using some additional experimental testing to generate the modeling parameters?
Okay, first, how do you model the reduced rebar in FEM software? Okay, that one, the shear wall vertical reinforcement, it is mainly decided based on the wind and SLE demand. But for the shear wall shear rebar, we decided based on the MCE shear demand, and also confinement relaxation also based on the axial strain results from MCE. So for the shear wall, vertical reinforced, because when we model the shear walls nonlinearity, we use the fiber modeling approach. So we model the shear wall vertical rebar fibers and also concrete fibers. So in the shear wall vertical rebar fibers, we discretize the shear wall rebar area and represent as the rebar fibers. For example, in that boundary zone, we have the rebar area of 1000 millimeter square. In that case, one fiber represent 500 millimeter and another fiber represent 500 millimeter square. But for the confinement effect, at the boundary zone concrete, we have to model the concrete fiber with the confined material stress strain curve parameter because it is material level. And in the middle portion of the shear wall length, we do not have confinement. So we have to model the concrete fibers with unconfined concrete material stress strain curve parameters. Then we check the fibers in those, we check the axial strain in those material fibers, whether they are within the limits or not. So for example, at the corner of the wall, we have the confined concrete fibers. And then we will see the axial strain is significantly high or not. Based on that, we relax the confinement. But we do not reduce the vertical reinforcement in the nonlinear analysis. If we want to, if the members are, because we already designed the minimum requirement based on the wind and SLE for the vertical rebar. If we reduce the vertical rebar in the shear wall, it will not satisfy the wind and SLE requirement. So we just relax the confinement requirements.
Okay.
So we do not use the ASCE 41 backbone curve in the shear wall. We use the material stress strain curve. We can use in both ETABS and Perform 3D, those fiber modeling.
Thank you so much, Mr. Aung. Mr. Danigo, hope that answers your questions. Maybe we're moving on to the next questions from anonymous attendee here to Mr. Aung. During the application of performance-based design on the new building, do we need to design the building to resist both earthquake and wind hazard, or we need to design by the governing hazard only? If it's the latter, how do we classify which hazard is more dominant without doing the non-linear analysis, considering wind and earthquake has a different lateral load assignment?
For the performance-based seismic design of the new building, we have to check for both wind and earthquake because some members may be governed by the wind loading. For example, if the building is located at the high wind typhoon zone and also high seismic zone, we cannot always assume that earthquake will govern the design. But if the building is located a very low earthquake zone and very high wind zone, maybe wind will govern that design. But anyway, we better to check both loading because depending upon the building configuration, if the one direction wind may govern the earthquake loading. So it is difficult to say.
Okay.
So normally we design the wind loading to design the building to remain elastic under wind loading. But for the seismic loading, we allow the nonlinear response and the strong earthquake. So we can use the nonlinear time-based nonlinear analysis in the seismic analysis. But these days, performance-based wind design is also start using for very special tall building projects, but not as common as performance-based seismic design.
Okay, perfect. Thank you so much for your answer. One last questions, probably this is like short answer. What is the purpose of doing wind tunnel testing for the building that you mentioned? It is used to compare with seismic force with the force, or doing it to envelop those force together?
Okay, so wind tunnel test is conducted to get the more accurate and reliable wind loading in our wind design, not to compare with the seismic loading, because code-based wind loading, we can estimate it for the regular shape building, and also it doesn't consider properly the surrounding building effects and also building geometry properly. And also the code-based wind loading has mostly they have limitations. They consider only a long wind response. A long wind response means the wind is in X direction, building will sway in X direction. But a crosswind response, wind is in X direction, but building is exciting in Y direction. That kind of response is not considered. So we have to conduct the wind tunnel test for the tall building projects. My colleague Zia will explain more details in his presentation.
Thank you very much, Mr. Aung. I'm sorry I had to stop the Q&A because we're a little bit behind the schedule. So thank you so much once again for your valuable contributions and for sharing your expertise on this topic. I have no doubt that the audience has gained important takeaways that will enhance their understanding of performance-based seismic design, especially for a high-rise building. Thank you very much. If there's like some questions left, we're gonna revisit after, okay?
Yes, thank you very much. If you have any more questions, you can forward those questions to my email so I can answer the questions.
Thank you so much.
Thank
Thank
you.
you for your time. All right, everyone, let's move on to our third keynote speaker, Mr. Davy Sukamta, who is here. So please join me in giving him a warm virtual welcome. Let me share my screen. Okay, Mr. Davy Sukamta will be sharing his insights on performance-based seismic design for buildings, focusing specifically for Indonesia experience. A brief introduction to our third speaker. Mr. Davy Sukamta is the founder and principal of Davy Sukamta and Partners, with over 4 decades of experience in designing building structures and foundations. Since 1978, he has led the structural design of more than 350 prominent projects and a respected leader in structural engineering. Mr. Davy Sukamta served as the president of Indonesian Society of Civil and Structural Engineers, or known as HAKI, for 15 years, and is currently a member of its advisory board committee. Since 2001, he has also been a peer reviewer for structure and geotechnics for Jakarta province, specializing in foundation and superstructure design for tall buildings and deep basement structures. Mr. Davy Sukamta continues to be a driving force in advancing structural engineering practices in Indonesia and beyond. So without further delay, let's give it up to Mr. Davy Sukamta.
Thank you, Pak Asdam, for the introduction. Siang, Pak Is dan teman-teman semua. Good morning. Let me share my screen. Okay. I would like to share my experience in the PBSD in Indonesia. This presentation is prepared with my partner, Nick Alexander. In tall building design in Indonesia, we have evolved from linear static to dynamic to nonlinear. The shift from prescriptive to performance-based design means to encourage engineers to prioritize performance objectives and increase emphasis on uncertainty and variability. We must acknowledge inherent uncertainties in seismic design. In our view, PBSD is an approach to obtain buildings that perform better than typical code-conforming ones. and an approach to design buildings that doesn't meet the prescriptive code but can perform as good as a code conforming ones. My presentation will consist of 3 parts. First, I will discuss the available codes for seismic design in Indonesia. Then I'll talk about the ground motion selection and modification in Indonesian case. And lastly, I will present 2 buildings designed by my firm. In Indonesia, we have several documents available to design earthquake-resistant structures. We need to understand codes are not generally written with tall buildings in mind. Tall buildings are a special class of structures with very particular characteristics and requirements. Long period, multi-mode behavior, significance of P delta effects, and the impact of failure is huge. Tall buildings normally have non-conventional structural systems. Coral and outriggers are often adopted as the lateral resisting system. And this system is not covered in the prescriptive code. So we must refer to alternative methods. In SNI 1726, section 7.6, we have the sentence to allow an alternative accepted procedures to be used. There are several guidelines available for PBSD. In Indonesia, we are referring to peer TBI and SNI 1726. Selection of recorded time series is a very important step in developing the site-specific ground motions. This is a recurring challenge for practicing engineers. Nonlinear structure response is often highly sensitive to the selection and modification of input ground motions. Seed motions shall be selected from events within the same general tectonic regime and having generally consistent magnitudes and fault distance as those controlling target spectrum, and shall have similar spectral shape to the target spectrum. The procedure conforming to SNI 1726 and SNI 8899 can be divided into 4 main steps. First, we determine the spectrum response targets. Then we select the ground motions. And the third is to modify those ground motions. And lastly, to apply the ground motion in structural analysis model. Referring to SNI 1726, the ground motion used is defined as ground motion on the surface based on maximum response spectral acceleration as the value of ground motion intensity. And I show you here is an elaborate flow chart for the selection and modification of ground motion. Indonesia has multiple seismic source types contributing to the hazard. Here we see various mechanisms: subduction megathrust, active shallow crustal fault, shallow and deep background. Majority of sites have multiple sources contributing to the hazard. We must study the contribution of each mechanism from the aggregation results at short and long period. Proportion of source type in seed motion must be consistent with hazard deaggregation to ensure collapse performance evaluation is consistent with PHA. When using multiple sources having notably different magnitude distance combinations, and each contributing more than 20% of the relative contribution to hazard at a period of interest, we must select a minimum of 5 records for each of these significantly contributing seismic sources, and a total of 11 suites. The intent of this multi-source requirement for ground motion selection is to allow for different characteristics to be reflected in the ground motions used for dynamic analysis. As required by SNI 1726, we select record pairs for each target spectrum that have general compatibility with the appropriate tectonic regime, the controlling distance, magnitude, and site condition, utilizing the result of the aggregation at periods relevant to the structural response. The periods should correspond to a sufficient number of modes so as to have a participating mass that is at least 90% of the seismic mass. We can use pure NGA West 2 to select shallow crustal ground motions. And for subduction, we can use pure NGA sub. Current practice in Indonesia involves scaling ground motion to match a uniform hazard spectrum using one or two methods: amplitude scaling or spectral matching. For narrow period range of interest, we prefer amplitude scaling. For wide range, we use spectral matching. This slide shows one example of ground motion selection and modification for a narrow period range of interest, ranging from 1.5 to 5 seconds. The scaling factor is about 1.9 to 3.9. And those time series are used for the analysis of a seismically isolated structure using friction pendulum in Jakarta. And this slide shows one example of GMSM for a broad period range of interest, ranging from 0.4 second to 18 second using spectral matching. The ground motions are used to analyze a super tall building in Jakarta. The spectral matching result must be verified so as not to have significant modification to acceleration velocity and displacement time series, and can maintain the area's intensity in the significant duration. There is some debate about whether spectrum match motion lead to a biased structural analysis result. But there are no objective or quantitative criteria available to decide whether a ground motion has been manipulated excessively by spectrum matching, or whether a large modification may also lead to a bias. Some studies, for example, by Arup Advanced Technology and Research, demonstrate that spectral matching does not introduce significant bias in analysis result when compared with a rigorous point of comparison benchmark. Now we look at two projects using PBSD. This slide shows several buildings developed by the Pakubono development groups, and among others is on the left side is the Pakubono signature, a 50-story, 253-meter tall building We designed it with a response spectrum method and revisited with PBSD in 2011. The lateral resisting system is RC core wall and outrigger, which is not in the prescriptive list of SNI 1726. The gravity resisting system is flat slab with drop panel. So the structural system for the building shall be clearly demonstrated to have well-defined inelastic behavior where nonlinear action is limited to clearly de-identified members and regions. All other members should be stronger than the elements designed to experience nonlinear behavior. We predict the inelastic actions from the result of RSC. Limited plasticity will occur at some locations in the core wall, at shear hinges at coupling beams, and concentrated hinges at base of outrigger columns. All actions must be classified as either force or deformation control. Force-controlled action must be further categorized as critical or non-critical. The goal of the analysis is to reliably estimate seismic response. All elements which significantly contribute to or affect the total or local stiffness of the building should be included in the analytical model, and to verify that their behavior will be acceptable. Because the goal is to estimate the central tendency of response, the model parameters, including structural stiffness and strength, gravity loads, and mass, should represent the central tendency values. For inelastic elements, we use fiber model and concentrated hits. For elastic elements, we use AEI crack and 2.5% damping. Basement structure is included in the model. The model is fixed at the mat foundation level. Free field ground motion is applied at the base. SSI is not included. Minimum base shear applicable. Inherent torsional properties of the structural system should always be considered. For confined concrete, we use Mander model. For coupling beams, we have two types, diagonally reinforced and composite steel plate for elements with higher shear action. And here we can see the global displacement of the structure in time series. The blue dots indicates the formation of plastic hinges in coupling beams. And now I will show you the result of analysis in succession, the accumulated core shear in X and Y direction, the overturning moment about the X and Y axis, the interstory drift ratio in both directions, and all are below the 3% acceptance criteria. And this is the global drift in X and Y directions. And compression and tensile strain at northwest corner of the core wall. Of course, we must check the strain on all wall components. The coupling beam rotation at N2 and W location, and later we must check the strain of all coupling beams. And this is the accumulated core shear at pier W15 and W1 and east. And also the axial force on northwest outrigger column. And this is the summary of the nonlinear time history analysis result. So we put this experience into a paper presented at the performance-based design workshop in the CTBU 8 2012. And later it was published as CTBO8 research paper. And now I will talk about the second project, Indonesia 1, currently under construction after being dormant for 5 years. The two towers, one is 63-story, and the other is 59, plus a cube structure sits on 7th-level basement structure. The buildings are located in Jalan Tamrin, a very prominent address in Jakarta. It reaches 303 meter high and will have 2 sky bridges. The lateral resisting system is RC core wall and outrigger. The gravity resisting system is steel frame with composite columns. Core wall plasticity is expected at 2 locations, and the core wall is modeled as fiber elements. And now I show you the result of time series analysis for 1 ground motions. And the green dots represent the formation of plasticines in the coupling beams. And now I'll talk about some construction aspects. We use a method called unequal height synchronous rise, where the core wall proceeds in front. And the design, of course, must consider the construction sequence and included that in the analysis. We install steel erection columns capable of taking the weight of 3-story bare steel frame plus 3-story steel frame and composite floors, and then encase them in reinforced concrete. The detailing has taken method of constructions in mind. For example, where to put the clammy pipe. And this kind of detailing helps in speeding up the constructions. And we use hydraulic climbing formwork with high capacity luffing jeep crane attached to the core wall and climb with the formwork. Since the pumping pressure is very high, more than 16 MPa, all the steel pipes must be fixed properly to the RC floor or RC wall. And we use special make high performance concrete, which must meet several criteria through several tests as well. The SCC must fulfill 4 characteristics as shown here: flowability, viscosity, segregation resistance, and passing ability. And now we talk about the sky bridge. So the design of sky bridge is a bit complex due to the non-parallel orientations of the 2 towers. So we need to transfer the forces from the truss to the core wall through a horizontal truss, steel plate, and shear studs. We have to be very careful with the load path. And at the end, the cantilever truss is anchored to the RC core wall. And this is how we transfer the forces from the steel truss to the core wall via steel plates and shear studs. And as you can see, the detailing is quite complex, so we have to use BIM to accommodate this complexity. And the design of the Indonesia 1 tower is performed by all Indonesians, starting from conceptual design to the forecon drawings, specification, and also site supervisions as resident engineers. For me, Ph.D. is about defining hazard and demonstrating performance level using rigorous analysis. Defining hazard means we must understand the tectonic setting of the project site, target spectra, and select the proper seed motion. And for my closing remark, structural engineering is the art to use something with uncertainties in its properties to build something with uncertainties in analysis to withstand something that has uncertainties in definition, and all for public safety. Thank you.
Thank you very much, Mr. Davy Sukamta. What an insightful presentation from our third speaker. As promised, we now open the floor for Q&A. So let me explore the chat box and see if we've got questions from the participants. First questions, Pak Davy. How many percentage in terms of the efficiency when we design the reinforcement using performance-based design versus perspective approach?
Okay.
Yeah.
I have a different view on this. If we want to achieve efficiency, in my opinion, it's not about just using a rigorous analysis. The concept is very important. The concept itself. Later, we have to prove that our concept at least not deviate that much from our prediction using rigorous analysis. If your concept is wrong, no matter what analysis type you use, you will not achieve the efficiency. That's my answer.
Okay, thank you very much. So I think the questions is also very similar. So in what level that the performance-based design approach can be more effective in terms of like the height of the buildings. So when we decide to use the performance-based design to design the buildings like that.
Okay, the previous speakers, Pak Iswandi and Pak Aung, has also mentioned that if we want to use an innovative structural system, but that system is not in the prescriptive code, so we have to apply this PBSD method. And by doing that, we can use the system which we think is best for the given project. For example, if your building gets taller, right, you cannot just use SMF. For sure, you have to combine that with shear wall or core wall. If the performance is satisfactory, then you can stay there. But the taller you go, you will see that the overturning moment in the core wall and also the period of the structure will be very high. And since we also have to pay attention to the serviceability of the building, for example, from the wind effect on the human comfort, for example, on the floor accelerations, we need to, say, have a quite stiff structures in order to have a good performance. And in that sense, if you only thicker, make the wall thicker, it's very inefficient. So we can use core wall with outriggers. And if the wind tunnel says, indicates or demonstrate that the performance is satisfactory, you can stay there. With taller buildings, you may have to use also belt truss, because belt truss will engage all perimeter columns to work together with the outrigger, but it's also more complicated. So if you need that you go that way. And if your building gets taller, maybe you will require an external bracing, right? So when we are going to use PBSD or not, it depends on you. If you are satisfied with one system, then that's fine. You have to use innovative structures, and it's not included in the prescriptive code, you have to use PBSD. There's no limit on the number of height or how big the building is. It's not relevant. For me, that's my opinion.
Thank you so much. I think one last questions, and this is a bit personal. What are the challenges or limitation of designing high-rise buildings using a performance-based seismic design, specifically based on your previous experience in building project like Indonesia One or Skybridge?
Okay, there are two issues now. One is on the say more fundamental ones is on the selection of the seat motions. Fortunately, PUPR and PUSGAN has established some guidance on that. The SNI 8899 on the selection and modifications of the ground motions, complemented with the book on the aggregations, which will help a lot on that. Other than that, on the practical side is on the running time, because we have to use 11 suites. So it is taking a lot of hours of computer runnings. And my advice is don't try to model everything as inelastic elements. You may end with a wrong result. So we have to predict first where the plasticity will occur. And we just model that part for the inelastic action. Other part can be modeled just as elastic element. And because it's elastic element, it will fall into, say, not a deformation control, but a force control component. You have some penalty on increasing the forces, but it will be not that say the penalty will not be that big for the cost. If the concept is right, then you are there. Thank you, Pastor.
Thank you so much, Pak Davy Sukamta. Thank you once again for your valuable contribution and for sharing your expertise on this topic. I'm sure our audience or participants has gained like important key takeaways from your presentation as well that will be beneficial in their understanding of performance-based seismic design, especially for the Indonesian projects. Thank you very much. So we're gonna continue to our last and fourth speaker, Mr. Zia. Are you there?
Yeah.
Okay.
Hi, good afternoon. I think it's almost afternoon there, right? Okay.
Okay, yeah. So
Yeah.
please join me in giving you a warm virtual welcome. So let me share my screen. Okay. So Mr. Zia will be sharing his insights on an overview of wind tunnel testing. So a brief introduction to our fourth and final speaker. Mr. Zia is currently the coordinator of wind tunnel testing and structural health monitoring at IIT Solutions. Mr. Zia completed his graduate studies in structural engineering from Asian Institute of Technology and specializes in wind engineering, structural dynamics, laboratory instrumentations, and digital signal processing. Mr. Zia is involved in projects of wind engineering, performance-based seismic design, and structural health monitoring. So without any further delay, I would like to give the stage to Mr. Zia. You may share your screen. Thank you very much. Perfect. Yeah, we can see your screen.
Okay. All right. So you already had several presentation on performance-based design. So this presentation will be more like a dessert of the session. All right. So topic of my talk is wind tunnel test, and I'll just give an overview. Now, let me start this. Okay, right. So let's talk about some wind effects on tall buildings. So for wind effects on tall buildings, there are three main components. One is cladding pressure. So in this video, you can see the John Hancock Tower, which is around 240-meter tall, 6-story building. In 1973, just after the construction of the structure, there was some wind event. And as you can see in this video that some window panes were replaced, and not some, actually a lot of them. And it cost about 5 to 7 million USD. And it happened due to some windstorm. But during that time, there was no mobile device that immediately when it was uh, failing during the windstorm. Nobody could make the videos. The video was made after the event. But these days, we can actually directly see when the event occurs. For example, this video is captured in 2021 in Karachi, Pakistan. You can see cladding failure due to wind. So this is one of the uh, problem for a building that its cladding may fail. Now, this John Hancock Tower, this building actually had several issues. One of which was building actually swayed in the wind, and upper floor occupants suffered from motion sickness, and it required some retrofitting. For that, they installed two thermos dampers, and that cost them about 3 million USD. And they also have to put bracings to suppress the acceleration response. So in total, 8 millions were invested. So the total cost of the project was about 75 million. So you can see that as they did not consider the wind tunnel test, so the additional cost was about 15 million. So we do not really want that. So it's better to go through some wind engineering work for this sort of a project. Now, how it feels like wind-induced acceleration, you can see from this video. It was captured in 2012 in Denver, Colorado in US. During a windstorm, the building vibrate, and you can see that from the vibration of this chandelier. So it can be quite scary if you are at the 40th floor and you can see the building is vibrating like that. And aside from that, another effect for the wind is the pedestrian comfort and safety. So you can see that these people actually in a certain location cannot really walk comfortably, and can be a safety issue also. When there are tall buildings constructed around, it can create some channeling effect, or tall buildings can create downwashing flow, uh, which can cause this pedestrian comfort and safety issue. Now, we have some design solution for this case. We can have we have building code. I just showed A.S.C. code, but not necessarily it has to be A.S.C. Just for an example. And then we can do wind tunnel test. And as well, we can do also CFD simulation. CFD stands for computational fluid dynamics. Now, our building codes have some limitations, but before explaining that, I need to explain the concept of wind-induced response, how it is accounted. So here I'm showing two time histories. Let me do this. Okay, this one is the force time history, and the next one is the conventional and response time history, you can say. So mean force actually gives mean response, and fluctuating forces actually give fluctuating response. We call it background response. But this fluctuating force actually have frequency content. When it matches with the natural frequency of the structure, our structure start to vibrate. And vibration of the structure actually generates inertia force. So the total response can be even higher. So the total response is actually coming from the mean force, mean response, fluctuating force is giving background response. And then this inertia force actually gives resonant response. So this is the basic concept of wind-induced responses. Now we can start looking at the limitations of the building codes. I'll explain few of those for today's presentation. So one limitation of the building code is it cannot account for the interference effect. For example, in building code, they consider exposure D, which means like open sea or flat terrain. And then they have exposure C, which you can say open terrain. It assumes that there are some small houses in front of your structure, but none of these are taller than your structure. And there are no buildings at the back of your structure if the wind is coming from this direction. This is the assumption in the building code. And they have exposure B, which means suburban terrain. So a bit more taller buildings in front of your structure, but none of them are taller than your structure. And there is no building at the back. But in reality, our structure is actually surrounded by structures of many different sizes and shapes and so on. And due to these structures, there is an effect called interference effect, and that is not accounted by the building code. And what it does is like it actually reduces the mean response. Some people call it shielding effect. So for example, if there is a structure in front of your structure, then there can be some shielding effect for which the mean response can reduce. But we often observe that it can actually increase the background and resonant response significantly. So overall response can be actually higher than previously, let's say, estimated where there is no surround building. So interference effect can significantly increase the building response. Well, in some cases, it can reduce a bit because if the mean response reduced significantly, then the total response can be reduced. But in general, it increases. Now, you may say, how about if we do some research and come up with an interference factor, and then we can use it in the equivalent static load so that we can account for the interference effect. For example, if this is your target building, we can put an interfering structure at the back or maybe at the front, or maybe we can put multiple interfering structure, one at the front, maybe two at the side, and so on. And then we can get response with interfering building and response of isolated building, and we can estimate an interfering factor, which we can incorporate in the building code. We have done a lot of research in AIT as well, but problem with that is our city is quite complicated. For example, if this is our target structure, it can be surrounded by many different structure of different size and different shape. For that, this interference factor may not really work. So that is why, even though the research on the interference effect started in somewhere in 1920, I guess, but still there is no interference factor you can see in the building code because our city is a bit complicated. And then moving on, another thing is the building shape. For example, this project is located in Philippines, so we worked on this project. It is given a shape of a Christmas tree. Well, our building code can actually estimate wind-induced forces for, if I say building, for specifically rectangular buildings. But if you have a building of a bit not so conventional shape, in that case, even though the building may not be so tall, you might have to go through the wind tunnel model test because you cannot really use the building code approach for wind-induced forces. And then how about a very conventional rectangular building? For example, in this case, a CRC building. We just want to figure out how it responds to the wind. So we measured pressure in the exterior surface of this rectangular building, and then we plotted a pressure contour, a dynamic pressure contour. So this one is the front, and this one is the right, back, left, and wind is coming from the front side. And this is the fluctuating pressure that we have plotted. And then we have shown drag force, lift force, and torsion, torsional force coefficients. What we can see from here, even though the wind is coming from the front side, as Mr. Aung discussed about earlier, wind is coming from the front side. So our expectation would be like the force would be only Fy. But we can also see the force Fx. This sort of a force is called across-wind force, or for that, the structure will have across-wind response. Most of the building codes does not account for the across-wind response. Even if any building code accounts for that, they cannot accurately estimate the across-wind responses. Another thing is, if you see the fluctuating pressure, you'll see the pressure is higher in one side sometime, then sometime it is higher in another corner, and then the distribution of the pressure is not uniform. And due to the non-uniform pressure, we can have wind-induced torsional response. So this is also not accounted in many of the building code. So in general, what happens is the building have to resist along wind response and torsional response at the same time. So we call it lateral torsional coupled response. So which we can actually account in our through the wind tunnel model test, not by the building codes. And aside from that, there are some other limitations in the building codes. There are some limitations on the height. There are some limitations on the natural frequency and so on. Now moving on, so the best solution that we can get as of now is the wind tunnel model test. So in the wind tunnel, what we do is we simulate the natural wind in a smaller scale. So I'll explain further. So we have spires and roughness elements. So we have a fan that generates a smooth wind. And when it goes through these roughness elements, we can have boundary layer wind. Then in the upwind location, we have the scale down model, and we also model the surrounding structures. And surrounding structures are to account for the interference effect coming from these surrounding buildings. And then we have the target structure. And from the measurement, we can get structure wind load, we can get cladding pressure, and we can also get some estimation on the pedestrian comfort and as well as for the safety. Now, this is our wind tunnel in AIT. This is about 23-meter long, and it can produce a wind speed of around 20 meters per second. This is one of the largest wind tunnel in the Southeast Asia zone. And in this wind tunnel, we have tested several structures. Over 50 projects we have done, and many of our projects are located in Philippines. Some are located in Cambodia, Pakistan, Thailand, and so on. And the height range is like from 100 meter to about 350-meter tall buildings that we have tested. And not only the buildings, we have also tested some complex structures like statues or bridges or even submarine ships and so on. And now I'll explain how this wind tunnel test is actually carried out. So we simulate the boundary layer wind. So we have these spires located at the back. And then on the floor, we provide some roughness elements to simulate the boundary layer wind. This dimension of these elements are actually decided based on trial and error so that we can match the mean wind profile and turbulence intensity. So these two parameters we have to match so that like the wind profile at the site, we can achieve it in the wind tunnel. Now, how we get the wind profile at the site, we can do it through the climate analysis. We have some software to do the climate analysis and identify the site-specific wind profile. And these two are the parameters that are used to identify the wind fluctuation and wind profile in the site location. Then we test actually for several configuration. For example, the figure at the left is showing the existing surround configuration. So this is our target building. Okay, this project is located in Karachi, Pakistan. So, and these are the existing structures. So in this location, this structure's already been constructed. So we consider for this surrounding configuration. And then we also consider the future surrounding configuration, because the client, they could provide us the information for some future construction in that location. So these buildings are also incorporated. So we tested for the existing surround and also for the future surrounding, and then the design can be done for from the envelope that is okay. Then in some cases, we find out that, okay, there are some very tall buildings which is outside of the test zone we have. In that case, we can also model these tall buildings which are far from our target site, so that we can accurately capture the interference effect that can cause some effect on our structure as well. Now, how the test has been done. First, I'll talk about the high frequency force balance test. So in this case, we make a high density foam model, which is very lightweight, and it has been supported by a carbon fiber pipe section. So the stiffness of the model is normally very high. We try to keep it over 100 Hertz. The name of high frequency force balance, high frequency comes from the high frequency model. And then we have a force balance at the bottom, which is a force sensor. And from from this sensor, we can actually estimate the wind-induced overturning moments and forces at the base. So at first, we get the measure the forces. As we measure the forces in model scale, we have to estimate the force coefficient, which is unitless. And from there, we can estimate the prototype forces. Now, this prototype force actually have the mean and background component. It doesn't have the resonant component to it. So we numerically add the resonant component, or we use the frequency domain approach. And then we can estimate equivalent static force along the height. So here I'm showing equivalent static force forces for 700-year return period. We can get the force Fx, Fy, and also torsional moment. This is for the ultimate strength design, but we also provide service level forces also for 10-year return period, and we also estimate acceleration response for 1-year return period. Now here I am showing some results of some tests we have done. So X line is like the number of projects that I have shown here. So here I have shown 31 of our project result outcomes. Now, this red dash is like baseline. This one is like, these dots are actually ratios of wind tunnel test and core prediction based overturning moment. MX is represented by green dots and MY is represented by blue dots. So this is a ratio of wind tunnel test and core prediction. So if these ratios are within this red line, it means like whatever we the result we have obtained from the wind tunnel test are actually matching with the results from the core prediction. But you can see the most of the cases, the forces we obtain from the wind tunnel test are actually lower than 1. It means from the wind tunnel test, you can actually achieve a bit economic design. But still, those results are safe, because in the building code, the force coefficients or the pressure coefficients, those are given, are actually for a synthetic scenario, and those are coming from the wind tunnel model test as well. But if you test your actual structure in the wind tunnel, you can get the actual result. So in that case, you can achieve a much economic result design, or in some cases, you can see that is forces are much higher. It can be even 1.4 or 1.5 times higher. In this case, you have to think like the results you are getting, actually, this is giving you safer outcomes, because in the winter, for the building code, it did not account for the interference effect and some other effects, which is accounted in the building code, which is accounted in the wind tunnel test. So the forces you have achieved can be sometimes higher also because of those effects. And then here I have shown 2 of our projects. One is at the left is in Cambodia. It is about 322-meter tall building. And at the right is an observation tower located in Philippines, which is about 200-meter tall. So this sort of a structure actually have a much higher acceleration response. So now I'll talk about some acceleration issue and how we can mitigate those. Not only these tall buildings, even a shorter structure, in this case, a structure located in Karachi, I'm showing like it had very high acceleration response. It height was only 150 meter. And then, as I explained earlier, this structure was tested for existing surrounding scenario and also for the future surrounding. For the existing, the acceleration response was high for most of the wind attack angles, but for the future configuration, it was significantly higher than the limit. Now here, I am showing the acceleration response for 1 year return period, and the limit I'm talking about the ISO acceleration limit for residential building. It's a residential project. Initially, we find out the acceleration response is about 1.81 times higher. Then we assume that, okay, how about if we increase the stiffness of the building by 1.6 by 1.5 times by adding bracing or maybe increasing the shear wall dimension and so on. But what we find out, the acceleration response have reduced a bit, but still it is about 1.63 times higher than the limit. Now, if you see the limit, you can see in the x-axis is the natural frequency. So when the natural frequency is low, it means when the structure is less stiff. In that case, you have higher tolerance for the acceleration. But when the natural frequency actually increases, which is increment of the stiffness, the limit actually reduces also. For example, the idea is when the acceleration is high in the higher frequency, and then when the actually the acceleration in the higher frequency have lower in terms of tolerance, and that is actually identified through some shake table test. Some experts are exposed to acceleration of different frequency, and then they give their opinion on which frequency, how comfortable or how discomfort they had the feeling. Based on those, actually these parameters are set. So you can see for the high frequency, the acceleration limit is a bit lower. So solution for this one is applying damper to the project, to the building. So for this particular project, we actually assigned two dampers. One is to suppress the translational acceleration, and another is to suppress the torsional acceleration. And as you can see, this green line is actually acceleration response, and this when there was no damper to the structure. And this red line is the limit, which is about 8 millig for this coming from the ISO criteria. X-axis is actually wind attack angles. We test the structure for 36 wind attack angles. So wind attack angle from 0 to 350 is shown. So almost for all the wind attack angles, you can see the structure had higher acceleration. And after we applied damper to the structure, the acceleration actually suppressed only at the 90-degree due to the across wind response. The acceleration found to be slightly higher than the limit, but it's still acceptable. Now for the dampers, there are many different types. Now for two mass dampers also, there are many different ways to apply those. For example, there is a pendulum type two mass damper installed in Type 101, which actually occupied about 6th floor. Actually, for a 150-meter tall 50-story building, this is not a economic solution. So in AIT, we did some research and we come up with a multi-stage steel laminated rubber bearing two mass damper, and we find out that this type of two mass damper actually can be more cost effective. It can save valuable floor space. So this is about the structural wind. So I talked about the forces, I talked about the acceleration. Now we'll move on to the cladding pressure study, which is another important fact. So for this one, we actually have to make a different type of model. So we use 3D printers to make this sort of a model. And then we install pneumatic tubes to this model. And those are connected to the pressure sensor so we can get the measurement. And then we test this one for 360-degree wind attack angle with the interval of 10 degrees. So for 36 wind attack angles, we test. And then we obtain cladding pressure outcomes. So here I'm showing peak pressure, peak positive pressure for this particular project. It is located in Pattaya in Thailand. I think it's very popular. Most of you already know about it. So the project was nearby a hill. So inside the wind tunnel, we also modeled the small hill. In case of small hills, we can model those in the wind tunnel, as you can see. And then we can also obtain the negative pressure cladding designed for positive and negative pressure. Now, cladding pressure study can be handy also. It can be used to estimate wind-induced forces as well. For example, this project located in Bangkok, it had a very long cantilever at the front here. It is about 24-meter long cantilever. Now, this cantilevers, due to the cantilever's location, we could not do the high frequency force balance test, as you can see here, because we cannot put the force sensor here. So we measured the pressure and we used another approach, which is called high frequency pressure integration, HFPI, to estimate the wind-induced forces for this cantilever section of the structure. So we used the cladding pressure. We measured the cladding pressure, and then we used HFPI technique to estimate forces for some location. And this pressure measurement can be handy for projects like this dome structure. So this one is a temple located in Saraburi, Thailand. So we measure pressure in 79 tap locations. And then this is the pressure contour. So once we measure the pressure, we apply this pressure to finite element model, and then we run the linear time history analysis for the design of this structure. And this structure has already been constructed and open to public, as you can see from this picture. And then there are some structures like stadiums we worked on recently in Philippines. So we had two structures here. One was an exhibition hall, another one was a stadium. We used the same technique to get the wind-induced forces. So we measured the pressure, and measured pressures were directly applied to the finite element model, and then the structure was designed. Now, you can also run the nonlinear time history analysis using the wind-induced pressure if you wish to do the performance-based wind design or not. The same concept can be applied for that. Now, aside from pressure measurement, one last thing we do is the environmental wind study. So we are back to this T-shaped structure. Here, we actually place a different type of sensor. We call it, actually it is called Arwin probes. But in AI solution, we call it Swapit probe. Swapit is one of our colleagues who actually construct these sensors. So there are some sensors that we can also construct in AIT. From this sensor, actually, it represents a human being of height 1.5 meter. So we measure pressure at the top, which is called dynamic pressure, and we also measure pressure at the bottom location here. So that is static pressure. So from the pressure difference, we can estimate the wind speed. And from there, we can identify if there is any discomfort zone in and around the building. For example, in the outside or maybe in the roof or in large balconies. For example, these dots are the locations where we have done the measurement. So we had the probes in this location. So in some location, we find out that the wind speed is good enough for the pedestrian sitting. And we identify that one by comparing our outcome with the Lawson criteria, which is available in the public source. And then we identify some location is pedestrian standing, some location is pedestrian walking, and so on. Now, if we can find some location, for example, here, if we find this one is uncomfortable for all users, in that case, we can actually apply windscreens, or we can plant trees around to reduce the wind speed. And that is the reason why you can see some shopping malls, specifically in Bangkok, if you come, there you can see many trees are planted here and there, may look like randomly placed, but those are actually coming from the wind tunnel test outcomes. So you can suppress the wind speed and make it comfortable for the users by planting trees or putting wind screens around. So that's all for the wind tunnel test. Now, another thing we can do is computational fluid dynamics simulation, CFD. So with the CFD simulation, you can achieve all the results that you can get it from the wind tunnel. You can get structure, wind load, cladding pressure, and also pedestrian comfort. But CFD have one limitation. Limitation is like you are modeling the wind based on some assumptions in your software. Okay. In the wind tunnel, we are testing in the wind tunnel, so we do not have to assume the wind property and so on. But here, as you are modeling in your computer, so you have certain assumption on the wind, wind flow, wind structure interaction, and so on. So that is why till this date, wind tunnel test is more preferred over the CFD simulation. But some clients come to us to do some environmental wind study using CFD simulation. So anyway, we can do the CFD simulation, but we need to be very cautious about it. Now, my presentation was mainly on the building structure, but there is another structure which is bridge structure are more vulnerable to the wind, and in the building code you may not find any information for the design of these structures. So, for example, in the left-hand side, you can see Tacoma Narrows Bridge. It collapsed in 7 November 1940. It collapsed due to a phenomena called torsional flutter. So, due to a very low speed wind, about 90 meters per second, this bridge actually collapsed due to the torsional flutter. And at the right, you can see the movement of the structure in vertical direction. So excuse me. All right. So if you notice carefully, you can see this bridge is actually vibrating in vertical direction. Okay, so these two are very important factor for a bridge. One is the torsional flutter, and one is a vertical movement. But we can identify these motions through the wind tunnel test. So this is one of the project we worked in Philippines. So we give some initial vibration to the structure, and then we identify negative aerodynamic damping, which actually causes the torsional flutter and also the vertical motion of the bridge. And that actually negative aerodynamic damping means once your structure starts to vibrate slowly, and due to the wind, the vibration actually escalates. It actually significantly amplifies and then come to a point then when the structure actually fails. And we can identify it through some flutter derivatives. We call it A2 star for torsion and H1 star for the vertical motion. And if we identify the structure is vulnerable, the bridge structure, then we can actually do some modification in its cross section. For example, this one is a bridge structure in Thailand. It's called Rama 8 bridge. So after the wind tunnel test, it was found out that the structure may not be the bridge structure can be vulnerable. So then the bottom part was enclosed, and so that it can give some aerodynamic shape to the bridge structure. And this bridge is in Japan. It's called Ajigawa Bridge. So you can see this aerodynamic shape is given to the structure so that it is less vulnerable to the wind. So yeah, that's all it is from my side. And thank you for listening. Thank you so much.
Thank you so much, Mr. Zia. What an insightful presentation from your side. So we've got like questions here from our audience. One is a bit lengthy, I may say. If you can check, do you want me to read it or you want to read it yourselves?
Okay, let me. Okay. Can we integrate structure health monitoring and performance-based design for the better resilience? Structure health monitoring can be integrated with the performance-based design as well. Yes, we can do. Okay, if so, how do we quantify robustness, level of damage after an earthquake, and rapidity to recovery to obtain the building resiliency index? For example, if we compare a single system building, let's say it's a buckling restrained brace frame with a dual system building buckling restraint frames, special moment frame. Okay, the dual system building most likely will have better energy dissipation, but the single system building will has its own advantage. Okay. Oh, I lost it.
Here, can I answer this question?
Okay, Mr. Aung
Yes.
can
Okay.
continue.
Yes. We can combine the structural health, integrate the structural health monitoring and performance-based seismic design. But in terms of resiliency, checking the functionality, recovery, and repair costs and downtime. So those things, if we want to check, we need to contact the resilience-based design. Because in performance-based seismic design, we still checking the public safety using more detailed analysis approach, but we do not check the functional recovery in terms of time. Time is a key component in resilience checking. So we are not checking the time functional recovery in the current PBD approach explicitly. But in FEMA P58, people start using for the building components checking for the functional recovery, considering the repair cost and repair time. So in that case, to check the building resiliency index, we better to go ahead with the resilience-based design together with the structural health monitoring. These days, the building codes are going towards the resilience-based design, not only the individual building resilience, they are targeting the community resilience checking. So in for structural, okay, another question is how do we know which structural system is more resilient? So it is difficult to quantify in the thumb rule. We need to check more details, checking because not only the structural damage, also the non-structural components damage and other details. And then we can say which one is more resilient. It is difficult to say actually, because resilience-based design is not is still evolving. Yes.
Yes. Okay. Okay. Next questions. So if we design a high-rise building to be wind tunnel tested, but the surrounding area is still empty, then how we could anticipate the effect of the future buildings to being constructed later?
Okay. Actually, in the A.Sc building code, I'm just referring to the A.Sc, and some other building codes also have some provisions that if you get the wind in loose forces, if it is coming from the wind tunnel test, if it is lower than the 80% of the building code, in that case, you have to use 80% of the building code results. The point of that is like, okay, you consider the surround building and then at some point, one of the building is being demolished. Or maybe there is a building constructed later on, which you haven't accounted when you do your wind tunnel test and so on. So for that one, actually A.S.C. building code, they actually give a provision that the wind forces cannot be less than 80% of the building code. So so that the design can still be safe. So that is one of the approach we follow.
Okay, thank you. I hope that answers your questions. And I think we have like final question here. So how do you analyze if the frequency of structure match to source of vibration? In another word, what do you think in resonance?
Okay, actually, wind, let's say wind-induced force, it actually have a range of frequency. All right, and range of frequency can be from 0.01 hertz to about 1 hertz in general. It can be higher also. Now, natural frequency of your structure can be in between at any point. And natural frequency of the structure we can obtain from the finite element analysis. And then we get the resonance for that particular natural frequency. Let's say for your structure, you have a natural frequency of 0.3 hertz. So we'll have resonance at 0.3 hertz frequency. All right. So we'll have the resonant force coming from that frequency. Additionally, what we do is we also consider 0.8 hertz and 1.2. 0.8 into natural frequency and 1.2 into the natural frequency. So after you construct your structure, if the natural frequency actually it comes a bit higher or a bit lower than the finite element model, normally it comes a bit higher, not lower. In that case, we can still account for those resonance, and then we actually give the forces for 0.8 into natural frequency and the natural frequency of the finite element model, and 1.2 into the natural frequency, so that we can cover the range of the frequencies. Now, how about over 1 hertz? If you see, go through the AC code, you'll find out they say the gas defect factor is 0.85 if the structure have natural frequency over 1 hertz, because the gas energy of the wind ranges from 0.01 to about 1 hertz frequency. But due to the interference effect, it can be higher also. So from the wind tunnel test, even if it is higher, we can account for the resonance for the shorter structure as well. But normally, if a structure have a natural frequency of 1 hertz, it's considered to be very stiff. So in that case, the response will be governed by mean and the background components.
Okay, thank you so much, Mr. Zia. Thank you once again for your valuable contributions and for sharing your expertise on this topic, especially like new topic for us. I'm sure like our audience has gained like important information from your presentation that will be beneficial in understanding the importance of wind tunnel testing, especially for super tall buildings and also long span bridges, as you mentioned. Thank you very much once again. So with all speakers done with their presentations, my time as the moderator of this amazing session has come to an end. However, before closing this webinar, I would like to take a moment to summarize the key insights we've gained from our esteemed speakers. So today we've explored the benefits of performance-based design in structural engineering, particularly its role in ensuring buildings meet desired performance levels during seismic events. This approach serves as a robust method to validate, optimize, and guarantee the structural capacities. This is especially critical in high-rise buildings where performance demands are significantly increased. So by prioritizing performance metrics over traditional prescriptive methods, an engineer can better control and enhance structural outcomes, ensuring safer and more resilient built environments. Also, we learned that wind tunnel testing plays a critical role in this process, allowing engineers to assess aerodynamic behavior, optimize structural performance, and enhance occupant comfort. So by simulating real-world wind conditions, these tests help refine design parameters, ensuring the building remains stable, efficient, and resilient under varying wind loads. Before I forget, there will be upcoming HAKI webinar in March 2025. Pak Andreas and team. So yeah, so for the participants, if you are interested, you can register with the barcode that is provided in the flyer. So yeah, so ladies and gentlemen, as we come to the end of this insightful session, I would like to extend my sincere gratitude to our esteemed speakers, Professor Iswandi Imran, Mr. Davy Sukamta, Mr. Aung, and Mr. Zia, for sharing their expertise and valuable perspectives. A special thank you to our participants for your active participation and engagement. I hope today's discussions have provided meaningful takeaways that will inspire further exploration and applications in your respective fields. With that, I'm now officially closing this webinar. Thank you. And on behalf of the Committee of Indonesian Society of Civil and Structural Engineers, or HAKI, we look forward to seeing you in future sessions. Thank you very much.
You.